Good morning, everybody. I'm Qi Wu, the Assistant Principal of Nanjing University of Aeronautics and Astronautics, and the General Chair of the 11th International Conference on Wireless and Satellite Systems, WiSATS 2020. On behalf of the organizing committee, I warmly welcome you all to participate in this virtual conference. Because of COVID-19 pandemics, it is great pity that we are not able to meet in Nanjing in person as planned. Fortunately, benefiting from the booming communications and networking technologies, such as 5G, we can still have this precious opportunity for interchanging ideas and opinions online. WiSATS 2020 is jointly organized by the Nanjing University of Aeronautics and Astronautics and Nanjing University. This year, we received about 200 submissions on various topics in the field of wireless and satellite systems. Ultimately, there are 86 wonderful papers accepted. We also invited 3 esteemed scholars to give inspiring keynotes on the future of wireless and satellite systems. It is a particularly exciting time to be involved in the research of a new era of information and communication technologies. I sincerely hope everyone can enjoy the program of WiSATS 2020. Thank you very much.
Dear ladies and gentlemen, let me welcome you to the EAI WiSATS 2020, the 11th EAI International Conference on Wireless and Satellite Systems, formerly PSATS. I am Aleksandra Śledziejowska and I am the representative of EAI. Unfortunately, due to the virus, I am not able to meet all of you in person, so I am using this opportunity to address the organizing committee, the authors, and participants on behalf of EAI. In particular, the general chairs Qi Wu and Biaobin Jin, and program chairs Trin Guo, Jiang Guo, and Jun Yangi, for their hard and excellent work throughout the whole process of preparations. During today's event, there are truly many ways how you can collaborate with EAI, and we invite you to try this partnership. Please don't hesitate to reach out to my colleague, Ms. Tsintava, if you are interested in cooperation in holding a conference or a workshop. You can see her email address just below the video. EAI as well provides you with the opportunity to ask questions and participate in Q&A sessions through Slack. Upon accessing the link below for WiSATS 2020 workspace, you can enter all channels which are divided into sessions. Moreover, you can vote on the presentations and leave feedback on your fellow presentations. You will get to determine which presentation will be the best from this conference. We will shortly show you how you can access these platforms. In addition, I would like to mention that after my presentation, my colleague Michael will talk more about EAI tools and also go into more details about the aforementioned voting, which you can make use of during this conference. To sum up, it is our honor to organize this year's edition of WiSATS. I hope you will have a wonderful time during this event and that you will follow the next edition in 2021. We will keep you posted, and the news about this event will be available on the conference website. We are looking forward to seeing you soon. Thank you for your attention.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier, and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu, And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Good morning, good afternoon, or good evening, depending on where you live. I'm Sastri L Kota, and it's an honor for me to give a keynote at this conference. I would like to thank Professor Kaglian and other organizers of this conference, WiSATS 2020. And thank you once again for attending this conference, especially for this keynote. "5G is in full underway around the world, and it attracted several stakeholders, including the leading information and technology infrastructure providers, academic research groups, standards organizations, and end users. The drivers of 5G include network, softwareization and virtualization, and massive MIMO ultra-densification, and end-to-end latency, which is phenomenally reduced compared to what the current systems are, and introducing the new frequency bands. However, the emerging applications and the use cases, the new technologies that drive the development of 6G and beyond, because of some of the use cases are not satisfied by the 5G at this time. I'm going to talk about these networks and the role of satellite and space in achieving these global connectivity. Let's talk about something about 6G vision, the drivers and KPIs, satellite role and architectures, new constellations like MEO and LEO constellations, and also the non-terrestrial networks to achieve the global connectivity, and what are the challenges ahead of us to solve and to address these use cases. So I will conclude with those challenges. This chart number 3, or the slide 3, shows the 6G vision. United Nations recently came up with the Sustainable Development Goals. From the economy point of view and social, and also the environmental point of view, to meet the demands and meet the new equity of education, for example, and also the all over the world having the equity of the economy, prosperity, and the peace, and the whole, considering the planet as it is. So to meet those sustainable goals, and also advancement of the information and communication technologies infrastructure, with the technology which is coming up, which is very prevalent to achieve these sustainable goals, is also the pervasive artificial intelligence. Those are all some of the visions of the 6G. Let's talk about the verticals, the drivers and the enablers meeting the 6G requirements in the slide 4. Say the healthcare, if you want to support in the rural and the remote areas fully, using the diagnosis, and also the treatment once you diagnose the patients, if needed, the surgery, which are all the drivers to come to enable the healthcare properly. The video streams and the virtual reality, augmented reality, the mixed reality, and also the terahertz band communications, sub-band communications also. It needs definitely, the requirement is the high throughput and the low power, at the same time the low latencies. Similarly, the autonomous cars, to have that business motive, the advanced sensors and the laser scanners, terahertz arrays for 3D images, and the enablers are the terrain mapping, for example, the route optimization, the safety, the data to be providing for the route maps to provide to the car drivers, which all need the larger bandwidth and very low latency at the same time, very high connection densities. So which is definitely the 6G requirements. The another application of this, or the business wise to look into, is the precision agriculture, which needs non-terrestrial networks. If you see on the same vertical business, the last one, which you see the non-terrestrial networks, which includes the LEO constellations, which are upcoming, which I will get to that very shortly, and also unmanned aerial vehicles, high altitude platforms. All combination of all these is the non-terrestrial networks. At the same time, to support the space IoT, or the space Internet of Things, Internet of Space Things, for example, to support those, the terrestrial offloading, which is the one of the enablers of this. Thirdly, to use the machine learning and artificial intelligence, which is the pervasive AI all over, that will help to achieve the precision agriculture. So the precision agriculture means the moisture, the soil moisture measurements, precise monitoring of the plant illness, the temperature, the humidity, all these, the data to be supported through, for example, a drone or a UAP, or UAV or a HAP or LAP, or any one of these, which providing non-terrestrial networks will support those precision agriculture. But at the same time, we need a larger connection density and the high bandwidth and the low latencies, which are the 6G requirements. Similarly, the smart education, the smart infrastructure are able to have in the verticals very good business wise, but the at the same time meeting the requirements of the 6G, which is the high bandwidth and the low latencies. Now this chart, or the slide 5, will show the 6G key performance indicators. If you look at the data rates, the 5G is only 20 gigabits per second, whereas it is almost 1 terabit per second in the case of the 6G. The experienced data rate is about 0.1 gigabits per second in 5G, whereas it is 1 gigabit per second, which is in the 6G. Similarly, the spectral efficiencies, 0.3 bits per second per hertz, whereas it is 3 bits per second per hertz in the case of 6G. The area traffic capacity is 10 megabits per second per meter square, whereas it is 1 gigabit per second per meter square. The connection density is phenomenal, 10 to the 6 devices per square meters, whereas it is square kilometers. in 5G, whereas it is 10 to the 7 devices for square kilometers. The latency is 1 millisecond, whereas in the case of 6G, it is 100 microseconds. So even some of the new architectures for using the satellite LEO satellites will try to meet some of these requirements, not as 1 milliseconds, but at least very phenomenally compared to the GEOs. It is going down and supporting some of the time critical applications. Similarly, the jitter is not specified at all in 5G, whereas it is 1 microsecond in 6G. The mobility is another important aspect of the parameters or the KPI, which is 500 kilometers per hour in the case of 5G, whereas it is 1000 kilometers per hour. So the 6G and beyond is going to support many of these applications which require the phenomenal high bandwidth and low latencies. Let us talk about the next few charts about what is the role of the satellite, why we are worried or concerned about the satellite, what is it going to bring to the table. The satellite, basically, the attributes include the ubiquitous coverage, especially to support the rural and remote areas for the communications or supporting the rural healthcare or the remote healthcare, etc. Definitely, you need the satellite or the non-terrestrial networks is the best solution. The bandwidth flexibility, using the narrow spot beams and the frequency reuse can deliver up to terabits per second. Once the satellites is deployed, the users can be added very quickly. The inherent nature of the satellites are the multicasting and the broadcasting. So that comes to the very good advantages to transfer the voice, the data, and the video streaming. And recently, many of you must have noticed that the airlines, many of these, either American Airlines or the United Airlines, the SAS, they're all trying to support the entertainment aspects in the aircrafts using the satellites. The disaster, I don't need to emphasize very much about how good and how the satellites are supporting the emergency communications and the disaster recovery. That is the best compared to the terrestrial segments. The reliability, of course, if you use the UR ultra low latency reliability communications mode, the reliability is the best from the satellite point of view amongst all the communication technologies. Now, the new coming and planned constellations of the LEO constellations, we are going to go through that, a few more charts on the what are the LEO constellations and the non-terrestrial networks are planned. They are going to definitely support the high bandwidth and the low latency requirements. So currently one of the major aspects of the 5G or the 6G is the software-defined networking, the mostly softwareization at the same time network functional virtualization, and that is possible even for the satellites use also. And as we're going to see in the next few more charts, that the high throughput satellites giving up till terabit per second satellites, and also for the Q and V and W, not only some of these bands, but if you see, we are going to talk about this. Amazon is going to plan using the E bands, that is U bands operation for the satellites also. So the machine-to-machine networking and also the data connectivity backup and the cyber resilience, these are all possible with the satellites. The mega satellite constellations such as the SpaceX, which the company started by SpaceX as the Starlink, it will provide a high throughput and low latency service very soon. We are going to talk about those two also. Currently, we have the satellite throughput anywhere until 140 gigabits per second, which is going to be in future the plan to from the Viasat or the LEO satellite systems with the Starlinks, etc., until terabits per second, or even the backhauling up till 10 gigabits per second. Now this chart, the chart 9 or the slide 9 is going to talk about some of the evolutions. I'm not going to, by any means, this is not the complete list of the satellites developed over the years. But the first one started with 1945 by A.C. Clarke's first extraterrestrial release. That paper revolutionized or started the birth of the satellite. Also, the Telstar, which was developed by AT&T in '62, it started one of the first satellites to support the voice circuits, 600 voice circuits and some TV channel. And then the Intelsat was formed, Eutelsat was formed. In 1978, the first internet access via satellite was done by using the Intelsat 4, the satellite, by none other than the Qualcomm CEO. He developed at the MIT, his team, Hoverston and Irvin Jacobs, have developed the accessing to the internet via satellite. That demonstration 78 proceedings IEEE, if you look at the paper, you can see that the whole results, what it has been done during that time. Similarly, the Iridium Global Star, as an experiment, they started the service on the LEO satellites, using the LEO satellite systems, 97, 98, and I was very fortunate enough to be associated developing the Iridium system at Lockheed Martin. But unfortunately, during the same time, the wireless communications has taken exponential growth. So the satellite systems, Iridium and Global Star and ECO, could not stand the competition with the wireless, and then they had to file for the Chapter 11. But believe it or not, the Iridium has been supported by the government for some time, and afterwards it came back. So now it is the second set of, or it's called the Iridium 2, being developed again, some of the satellite systems. And similarly, the Global Star, they come out of the woods. Now, 2003 is a very interesting year for all the satellite work. The Ka-band satellite systems, which are going to talk about within the next few charts, is developed, but at the same time, many of the satellites at the Ka-band, which was after even building the satellite system, could not go through the whole thing because of various other reasons. I'm going to get to that, what happened during that time. The advanced EHF, which was still active and it is working on, it has been studied, it launched in 2010, and earlier to that, it took almost like these are the geo satellite systems, and then before that, it is a Milstar is one of the mission objectives are different, and it has been the developmental cycle itself is a few years, 10 years almost, and it was launched further. Then there is an IP-based satellite was started, but it will never went off. Anyway, this is the 2011 Viasat started one, and 2017 Viasat-II was launched, and they are planning to have a terabit satellite system, high throughput satellite system. Now 2013 is a O3B, which is still functional, and then an interesting one, which we are going to go through the details on CubeSat, which is about 10 centimeters cube. That is going to be very cheap, and it is very applicable for surveillance and reconnaissance, etc. We can use that. We are going to go through those details. SpaceX started in 2018. The Starlink is a company started by the SpaceX itself, and it has a very large, ambitious plans. We are going to go through that. Anyway, this chart on slide 10, is going to give a basic idea or the concept of the satellite system, which is the space segment in this particular picture where the two satellites are interconnected by inter-satellite links. Normally, in most of the satellite systems these days are planned to have inter-satellite links to have an autonomous operation on the satellite itself. And also it has the terminal segment with all the baseband equipment and the terminals. It could be the fixed or the mobile terminals, and also the control segment. The control segment is all for the payload configuration, terminal configuration, planning, communication resource planning, resource monitoring, etc. Those are all, and also overall the satellite system control itself. So these are the basic system concepts for almost all the segments, the space segment, terminal segment. Sometimes you have the terminal, not only that, along with in the commercially, you can have a number of gateways also. So those are all the basic system segment, whether it is GEO or LEO, still we have to do this. The slide 11, it talks about the multi-layer architectural concept. As you see here in this picture, we have a number of the GEO satellite systems, then the LEO or the MEO satellite systems, the blue color which you can see, and also the pink color, the LEO satellites connected with the specific and also the non-terrestrial networks, which means high altitude platforms, HAPs, and unmanned aerial vehicles, which are the UAV fleet. They are all connected. The terminal segment, the ground segment or the terrestrial segment will consist of the terminals, the fixed or the mobile terminals, at the same time the gateways, and each one the overall the low, if you look at the pink satellite systems, they have connectivity with the low latency links for a multi-broadcasting. And also some of the inter-satellite links are connected through internodal links, as you see INLs in this case. So this way, there are anywhere from the broadcast nature or the broadband, high broadband nature to the very hotspot, a very specific narrowband purposes. Still the satellites could be connected. This is and also the number of satellite sensor networking can be performed in this. Navigation positioning systems could be, Earth observation systems could be provided through the satellite systems, and also the air traffic management should be done properly. Now the same thing summarized, we did talk about this communication, navigation, and Earth observation purposes, and it could be GEO, MEO, or LEO satellites. Possibly in future, we'll see more and more of the LEO satellite systems, the mega constellations as we talk. And high altitude platforms, unmanned aerial vehicles are connected with the non-terrestrial networks. High capacity fixed mobile relocatable gateways are part of the ground relays, could be part of the terrestrial infrastructure. The distributed antenna systems, the position devices for navigation, location-based applications, sensor devices for monitoring applications, and the functional framework of this is the broadcast to hotspot coverage, broadband to narrowband access, and also the onboard processing. One of the major importance of the design aspects of the systems are, should we have not only how many satellites, at the same time what altitudes and what type of systems they want to do. Is it a GEO or LEO or MEO? But at the same time, is the payload is an onboard processing payload, or a regenerative or a non-regenerative or bent pipe repeaters? So it all depends on what kind of processing satellite or the payload which you would like to have. At the same time, if it is a processing satellite, then you have the routing, and also resource allocations are done on the satellite itself. So it autonomously, but at the same time it has a negative effects also. It might be costing more than the other side. So it is a matter of trade-off within the designs what you want to do. Now, next few charts, we are going to talk about the current new constellations. What are the planned constellations? Could be most of them are the LEO constellations. So why this new wave of these LEO satellites? If you look at this slide or the slide 14, the satellites are the LEO satellites, low Earth orbit, medium Earth orbit, and the geostationary orbits. Normally the altitude of the LEOs are 700 to 2000 kilometers, whereas it is 10,000 to 15,000 kilometers for MEOs, and it is 36,000 kilometers for the GEO satellites. And one propagation delay is around 5 to 20 milliseconds for LEOs, that is a very low latencies, whereas it is 100 to 130 milliseconds, whereas it is one-way delay is 250 to 280 milliseconds. So there is an argument all the time between GEOs and the LEOs. The delay is very less in terms of the LEOs, and whereas it is very high in terms of the. But it all depends on the time critical systems and the non-critical, near real time, non-real time, and the data propagations. So it all depends on the type of applications what you are looking at and what type of satellite constellation you want to use it. It all depends on the design aspects, the business motives, and also the objectives of what the system you want to plan. Now to cover is the Earth coverage or the global coverage. Definitely we need more than 32 satellites for the LEO case, whereas it is 10 to 15 for the MEO, and also with the 3 GEO satellites we can cover the entire globe. Now, as you see here, most of them could be the onboard processing, which is possible, and they could be used for broadcasting and this satellite news gathering, etc. Now this slide 15, I just want to make a quick point about it. I don't want to dwell about all the satellite systems here. There are all 5 different types of systems, not only in US, but in the Europe, they developed not only the GEO satellites, the LEO satellite was also developed at some point of time. So this is in 90s, as you see. The Spaceway, Astrolink, Aeroskyway, Teledesic, and Eutelsat were developed, and but unfortunately, most of them are the GEO satellites except the Teledesic, which was planned as a LEO in the beginning. It was supposed to have 820 satellites, the LEO satellites. Many of these, Astrolink was developed by Lockheed Martin, and Spaceway by the Hughes Networks, and the Euroskyway is done by the European community, and the Eutelsat is still, I think it's existing. That is also done by the Europe. So based on all these, Astrolink, fortunately I was associated, I was taking care of the networking aspects of the system. We built the whole system after spending 5 to 6 years, and even the satellite was built, but this was never launched. None of these satellite systems were launched. The Spaceway has to change completely the direction of the satellites. Now they support the direct TV and so on. But other than that, the original plan was completely changed. Astrolink is never flown or deployed. Euroskyway, the same thing. The Teledesic, even though they started with the 800, we did some studies for them as a contractor for them on a specific contract. We came up with 200 to 300 satellites could be meeting the requirements what they planned for. But at the same time, this Teledesic was started by Bill Gates and also Macau. They both started this whole program. After funding the whole thing, spending for a few years, they couldn't handle this. They couldn't deploy the program. Then the Motorola took it over. They bought it, and then the Motorola changed the entire design from the LEO to MEO's constellation. And they were trying to build with 30 satellites, they can meet the requirements, but they couldn't handle. Finally, the whole slots were all given away, and even from the ITU standpoint. The point is, why it happened? They're all the Ka-band systems. Why did it happen? After spending billions of dollars, we couldn't handle the systems, we couldn't deploy the systems. Why? Because at the same time, there are several factors, not because of the technology. Technology is one of the best technologies that came up with the new thinking, new progress, new designs, everything. But there is a very timeliness factor. During that period of time, the wireless has a phenomenal growth, exponential growth, and then satellites could not stand the competition and they have to give away. So that's what happens whenever there are several other factors for the success of the business, not necessarily the technology. Now, there is, as we mentioned a little while ago, about the WiSAT, which has been this is from the Calabasas in California. They are Southern California. They are building these high throughput satellite systems. The first one is WiSAT 1 and 2. They're all planned. They're already launched, supporting at least 300 gigabits per second, even WiSAT 2. And the WiSAT 3 is planned to have 1 terabits per second with 4 satellites, which are probably will be launched by the end of this year. And then they also support of the flight connectivity in commercial airlines, United and Qantas and SAS and American and JetBlue, etc., where for the entertainment purposes, the WiSAT supports this. Now, the next couple of charts, I want to go through what the current satellite systems. These are all the LEO systems, mostly, except one, O3B, as you see here. But the rest of out of all the 7 systems, which I showed as an example, basically they're all the LEO constellations, the mega constellations. Why I call this mega constellation is because the data rate is 1 gigabit per second in the O3B, whereas the download speed is about 11 to 60 megabits per second for Starlink, and upload speed is about 5 to 18 megabits per second. And the number of satellites for of course, the Telesat is 1.2, and Amazon is planned for 781 megabits per second, and 10 to 30 gigabits per second Facebook, and OneWeb, of course, 50 megabits per second, as well as the LeoSat until 5.2 gigabits per second. But they're all planned for having a larger number of satellites, as you see here, about 20 for the O3B, which is the MEO satellites, and then the SpaceX, which is the company, is the Starlink company, going to have already, as of we speak today, the August 18th this year, we have around 648 satellites were launched. And they planned, the FCC has approved for 12,000 satellites for Starlink. And they applied for FCC approval for 42,000 satellites. Are you talking about the thousands of satellites? That's why they call mega constellations. So the Telesat is about 298, whereas the Amazon plans to have 3,000. Then the Facebook plans to have 42. And the OneWeb is around 720. Unfortunately, the OneWeb and the LeoSat recently filed for Chapter 11, but at the same time, I heard about OneWeb very recently. They approved, the FCC has approved another 1,200 satellites for that. And not only that, some high tycoon from India has supporting this OneWeb, and they are out of woods, I think, and we have to wait and see what's happening. I'm pretty sure this LeoSat also, they will find the investors and they will come out of this and they will make it successful. The latency in all these situations is about O3b is about 140 milliseconds, whereas it is Telesat is about 30 to 50 milliseconds. Low latency, but whereas in the Amazon, Facebook, it is early for them to talk about the latency aspects, but there is 20 to 30 milliseconds in the other two cases. Now, if you look at this continuation of the next slide of 18, the orbit is the O3b is the MEO satellites, whereas all the others are all the LEO satellite systems. The frequency bands, they're all Ka bands. SpaceX or the Starlink is supposed to have Ku, Ka. The Telesat is C, Ku, Ka supporting, and whereas the OneWeb is Ka, Ku. Other than that, the others are all Ka band. And they all have, except one that O3b would like to supposedly want to have the Amazon is not having not planned, at least at this time, on having a onboard processing, but the rest are all, they could be a bent pipe repeater probably. And then the Amazon and Facebook, they plan to, the Amazon plans to 2026, whereas the Facebook wants to have it by end of this year, 2020, and SpaceX want to have the service operations by 2020, whereas the O3b is already launched and it is the service in business. So the next few charts, we just want to show the type of architectures where they have. And I would like to say that O3b uses the frequencies 17.8 to 18.6 gigahertz and also 18.8 to 19.3 gigahertz for downlinks and telemetries, and also 27.6, 28.4 gigahertz and 28.6 to 29.1 gigahertz for uplinks and command frequencies. They are supposed to have 20 satellites launched till today. This is a very interesting Starlink program. It has already approved 12,000, as I mentioned earlier. But the interesting thing is some of the FCC submitted documents reveal that 4,425 satellites would like to have at 700 miles up, and another of 7,518 around 210 miles. So that the different altitudes variations would help. The SpaceX is also applied for 42,000 satellites. Well, the interesting thing is, if you look at the current literatures on Starlink, they call that as the terminals as the pizza box. So that must be the very smaller size on the satellite terminals. Now the Telesat, this picture shows that there are 117 satellites, 6 planes at 12 satellites each, and 5 planes, inclined planes, with 9 satellites each. And they're all with the Ka band, and it has the optical crosslinks between satellites. The launch is supposed to happen in 2021, and the beginning of the service is 2022. Now the CubeSat is the one which I didn't talk about earlier. Is one of the most promising for the type of 6G or beyond 6G and the future communications with the satellites. This is a nano satellite, it's called, with sizes ranging from 1U to 6U, whereas U is 10 by 10 by 10 centimeter cube, and typically weighs less than 1.33 kilograms, or at least 3 pounds per each U. So it is mainly to have the Internet of Things or the Internet of Space Things, for example, if you want to call it, and also to the machine-to-machine communications, and also the Earth sensing and also positioning purposes. These are all very well used. It has the most advantage of this is the developmental cost. Normally for a geo satellite, it takes anywhere between 7 to 10 years to develop before we launch launch the satellite and also start servicing. Whereas in this case, the low cost, the small size, and also less developmental time, that is the most important. For the launch cost also very less. So this planned service for this is 2023. Already there are some of them are being used. Even they can use it S-band even for some specific purposes. I'd like to talk as an example on this slide 24, just to show you basically what is this non-terrestrial network example. We did, as you see here, we did some study, and also we applied some of this activity, and this paper as the reference, if you look at it, is given in Dresden, one of the conferences in Germany last year. And it consists of basically GEOs or the MEO or LEO satellites. It also has the unmanned aerial vehicles and also the high altitude platforms. Normally it's about 20 kilometers, whereas it could be a few kilometers for the labs purposes. On demand, like the drones, we did study. Say an example, if you can take, is the precise monitoring of the physical parameters in the case of the farming example, where you like to have the temperature study, air pressures, and the humidity and the plant illness conditions, and also the real-time control of the plant and fire alarms. As an example, I can tell you that Tuscany is in the Italy. That area is a beautiful wine country. At the same time, there is a multi-billion-dollar business of the wines, preparation of the wines. But at the same time, the fires are so often, and to study that, to predict the fires and to study those things, this kind of a drone study or the non-terrestrial networking is extremely valuable to those. So similarly, recently we had here in California, which are also some of the prone to the fires, and it is devastating. Absolutely, lots of millions and billions of dollars are wasted. So some of these studies should be applicable in those things to predict the air pressures and to take some immediate actions for those. Now, let me digress 1 minute about what we are doing at this point. I want to tell you, to share with you guys. The IEEE has started one of the activities of the future networking, the International Network Generations Roadmap, that is the INGR study group. And last 2 years, we have been working on this 5G and beyond the networks. And last year, we published a report on this, and then we are continuing this year again to study more details on this and also develop a roadmap. What are the basic challenges we have at this time? What is the current within 3 years, 5 years, 10 years? What happens to the satellite or the systems itself? So this is the 5G and beyond networks. We have about 35 members right now, and every alternate Fridays we have the meetings, and at least more than 20 some people are committed to do this, and then we are working on this. This chart 26 shows the time schedule for and there are also the roadmap topics include the applications and services, reference architectures, and the MIMO, massive MIMO based on the physical layer studies, antenna designs, the artificial intelligence and the machine learning applications, and the edge computing, quality of service, quality of experience, security aspects, and overall network management. And also IEEE is very much interested, just as any other. We are going to go through a couple of charts as an example on the 3GPP, 5GPP, HC, etc. for the standardization activities. So one of the major, if you look at from a technology point of view, what is the big difference for the 5G and the 6G and the future networking, what happened in the previous networking. And so far we have come up with all the last 40 some years we built the systems and the network systems. What is the major is the virtualization and also the software defined networking. So this chart of 27 will provide you just an idea about the 5G and the beyond, or the 6G will still be able to handle various aspects even with the satellite systems itself for the exposed control interfaces, management or the data plane, and satellite gateway functions. These are all can be done with the satellites and also virtualization. So that is the idea of this, what can be done, just to illustrate the point that satellite aspects also can be done with the both the RF subsystems or the satellite gateways, and the terminals can be built in terms of the both network virtualized satellite network, at the same time the software defined networking. Now the next couple of charts I would like to talk about the challenges what we have ahead, especially how is this pervasive communications, the pervasive AI is going to solve the, is it something everybody is talking about, or is it going to be solving a lot of good problems? I wish that with all my current thinking, we definitely solve some of the issues, and it makes it much easier to solve the problems, as because we are talking about the densification, ultra densification with the high bandwidth and the low latencies, which we never had that kind of thinking earlier. So if you look at these applications, the positioning, network planning and routing, physical layer communications, the resource management, these are all the applications where the AI or the machine learning could be applied. Say, could we use for the supervised or unsupervised or reinforcement learning? So, for example, if you look at the reinforcement learning, we can develop the algorithms for these. To also, we can develop the routing algorithms. We can use the techniques for the resource allocation. Whether it is in the ground systems or in the satellite system, it doesn't matter. Wherever we have, once we develop the algorithm and deploy, we can use it for the processing payload if you want to. And also the adaptive coding and modulation, which is a very useful and helpful protocols. So the applications, it could be the image and the video delivery, or the situational awareness, or the traffic predictions. And the positioning could be the mobility, which is important, as we talked about a little while ago, about the 6G is 100 kilometers per hour, and the trajectory designs, the path selections, the network planning and routing, the multiple access routing handovers could be taken care of, and interface management and channel modeling, spectrum allocations, and also adaptive configurations as a part of the physical layer communications. Now the resource management, energy, power management, data caching, which is already some of the backhauling is being done as a standardization for the ITU in the radio sector. So we are having a phenomenal growth for the algorithms development and applications of the for the different types of applications. The ML, the machine learning, as well as the pervasive AI could solve many of our problems. This is another example just to illustrate the same point on the resource allocation on the chart 30, whereas once you know the considerations for the LEO is basically the constrained energy, the mobility, and the dynamics of the connections and the transmissions. The considerations which we start thinking about is the number of channels and the beams and the time slots, and what is the power allocations, the maximum transmission power for the satellite or for each beam, and the transmission power of one channel, and then the maximum blocking. These are the parameters in terms of which you want to develop an algorithm to solve the to address the issue of the resource allocations. Now, the next couple of charts, I just want to touch base with the research challenges ahead we have to address either 6G or the beyond, even the 6Gs. The new mega constellations of the satellites with respect to the LEO orbits and different frequency bands and the onboard processing, those are all the trade-off parameters which we need to do. Similarly, the non-terrestrial network architectures with LEO satellites at the same time with aerial vehicles, unmanned aerial vehicles, UAVs, and high-altitude platforms, which we need to study. The spectrum sharing in terms of the Ka, Q, or V, or E bands different. But at the same time, nothing comes easy. We have the rain attenuation problem in those things once you go up into the frequencies. So how do you mitigate those? What kind of the adaptive antennas and the modulation and coding type of things, how do you specify those? So these are all the various design challenges which we have. Integration with respect to the 6G. Basically, we have the satellite at the same time terrestrial. Mind you, this satellite is never a competition for the terrestrial segment, but it is the integration with respect to the terrestrial. That is how we want to address as an integrated networking architecture, as a non-terrestrial architecture to solve, to apply to the various applications and to solve the issues where the satellites has the niche market, like in the remote areas and along with the urban areas, not only that, but the remote and the rural areas where they have. And also the air interfaces has to be developed. The artificial intelligence, as we talked about as an example, has a lot of promising opportunity for the future to solve. And the latency is a big problem. There are so many applications where with the 20 milliseconds or less than 20 milliseconds, like the Starlink is already beta testing of their systems, which they demonstrated about 20 milliseconds in that with the LEO satellites. Now the quality of service issues, quality of experience with reliability, and the resilience with integrated systems, we can still have some of the issues to worry about. The protocols are integrated satellite and terrestrial network, at the same time the network management, resource management, handover protocols, which we need to develop, and also the standardization is a big aspect for either with the IEEE or ETSI or the ITU-R or ITU-T, which you are considering in various 6G quality of service or AI, ML. All these we have to develop the standards, not only the propagation, which the 3GPP is already doing. So this next two charts, I just want to illustrate the point of the standardization, the importance. 3GPP at sea, they're all 5GPP, they're all working on these, and this provides you an integrated network architecture design, research to prototype development via WP5 validation and demonstration, and the dissemination and the standards exportation. So these are all giving you the process how we start thing. But it depends. This is just as an example I just wanted to show. So this chart illustrates the various things currently what has been done in the 5G, and also we need to do different things as the 6G as well are in the future. So some of the activities, some of the organizations which are very active in this is 3GPP. 3GPP came up with already release 17 with the new development of the integration of the satellite access for the non-terrestrial networks. And the 3GPP came up with the study of the non-terrestrial and also the propagation models. 3GPP 16 has studied this evolution of the NR to support non-terrestrial networks. ATSI is doing the ECC has developed the satellite solutions for 5G. ITU-R, ITU-T, they both are working with the integration of the satellite system through the next generation access technologies. So this is various activities already fixed in mobile systems as well. And we need to continue and standardize for the next 6G and the beyond. What are the takeaways out of all these so far what we talked about? Number one is the LEO mega satellite constellations as a part of the 6G and beyond and the future networking to support and also to meet the SDG goals both in the economy, social, societal, and also the environmental aspects of it to support fully in the rural and the remote areas. Satellites is the best and the space IoTs can be supported. Number two, the non-terrestrial networks is an excellent opportunity, including the UAVs and the HAPs, and also some of the applications like drones, as we see already, to support the services, the 6G new services which are coming up, and with the phenomenal traffic growth and the ubiquitous coverage and the machine-to-machine communications, and also Internet of Space things, for example, and the best is the non-terrestrial networks. The thirdly, to come up with the integrated networking architecture to support the broadband and a very reliable and high reliable communications support with a seamless fashion to integration with the terrestrial networks. Lastly, the 6G and beyond the satellites have to develop the standards with collaboration with the academics, industry, and the research laboratories with various organizations which are very active at this point. And this is all what I want to share with you. And I thank you once again for patiently listening to this talk. And at the same time, I like to appreciate the organizers of the conference, especially the WiSATS 2020, for giving me this opportunity. And thanks once again.
Hello, everybody. This is Geoffrey Ye Li. I'm going to give a talk on deep learning in communications, which will provide an overview of what we have been done in the previous 4 to 5 years in my research group. First, please allow me to introduce myself. Currently, I'm a professor at the Georgia Institute of Technology. Before joining Georgia Tech, I worked at AT&T Belknap for 5 years. My current research area is in intelligent signal processing for communications. In the previous 20 years, I pioneered OFDM and MIMO for wireless communications. I established the Resource Corporation for Wireless Networks. My research impact is reflected by IEEE Fan Award in 2006 and journal paper awards recognitions from IEEE ComSoc, Vehicular Technology Society, and Signal Processing Society. In particular, I received 2019 IEEE ComSoc Armstrong Achievement Award. I'm also highly cited researcher since 2011. Here is the outline of my talk. After briefly introduced why should we use deep learning for wireless communications, I will talk about deep learning for physical layer processing and resource allocation. And finally, I conclude my talk and provide some future research topics. So, back to several years ago, when I tried to study machine learning for communications, I keep on thinking about why should we use deep learning for communication. And after thinking for a while, we figured out the following things, following issues which bring us to communications. In the traditional communication system design, mathematical model or accurate model is required, but in the reality, accurate mathematical model is very hard to obtain. Also, current communication system is designed based on block structure, and it's hard to get global optimization. And also, there are also like a complexity performance issue. And if we talk about the resource allocation, the problem is even more complicated. Based on the above issues, we're trying to introduce deep learning for communications. And with deep learning, accurate mathematical model is not necessary because we can use deep learning model. Deep learning model can learn from the data and learn the system feature directly. And also we can design end-to-end loss optimization for global optimization of the transceiver. And we can also have a chance to reduce the complexity and improve the performance of physical layer processing and resource allocation. So in this figure, we show the traditional way of design communication system. Traditionally, transceiver consists of many blocks. For example, in this simplified diagram, we have error correction coding at the transmitter, we have decoding at the receiver, and we have modulation at the transmitter and decoding at the receiver. And each block is designed according to its individual metric. For example, whenever we design coding and decoding, our metric will be the block error rate or bit error rate. However, when we perform modulation and demodulation and signal detection, and our metric turns to be the minimum mean square error. So because of that, it's very hard to jointly optimize signal detection and decoding to get the optimal system. And with deep learning, we can improve the communication system in the following ways. We can use deep neural network to substitute one or two or more blocks at the transceiver to reduce the complexity and improve the performance. Or we can use one neural network to substitute the whole transmitter, another neural network to substitute another, to substitute the receiver. In that case, we are performing end-to-end communication. So with this structure, and we have a chance to perform global optimization of the transceiver. Okay, this figure indicates the potential applications of the deep learning for communications. We can still keep the current block structure for the communication system design. And in particular, we can use model-driven machine learning to improve one or two modules in the previous slides. We can also perform using model-driven technology to improve the performance of each individual block, or we can perform the optimization in end-to-end manner. And in the next, we are going to give us 3 examples on each category. One example is model-driven deep learning for communication. Another example is end-to-end transceiver design. And I also give a data-driven block structured communication system design example. Deep learning, of course, can be used in wireless resource allocation. Traditionally, wireless resource allocation problem is formulated as an optimization problem. Then we use a mathematical method to solve the optimization problem, which is usually very complicated, and it's very hard to get the global optimal solution. We can usually get no complexity, but a suboptimal solution. With deep learning, we can help to reduce the complexity to improve the performance of formulated optimization problem. We can also use deep reinforcement learning to directly perform resource allocation for communication systems. In a subsequent talk, I will give 2 examples, one for each category. First, let's talk about the physical layer processing for deep learning for physical layer processing in communication system. So the first work is the power of the deep learning in physical layer communication. This is my first work actually, which demonstrated a power of deep learning in communication systems. I started with the channel estimation and signal processing, signal detection here, back to 5 or 6 years ago. And in the area of the channel estimation, we have like channel minimum mean square error channel estimation approach as we developed about 20 years ago. We also have some work on deep learning for example, for equalization and for decoding and so on. And the critical challenge here is how can we deal with the nonlinear distortion of channel and how can we deal with the interference. With the machine learning, we can perform joint channel estimation and symbol detection to improve communication systems. And with deep learning, the design system is robust and insensitive to nonlinear distortion and interference, as we can see from the subsequent simulation results. This is the traditional way to perform channel estimation and signal detection in OFDM system. This is our work, which has been done about 20 years ago. And this is actually a traditional paper right now in the area of the OFDM. This is a simple OFDM system, and this is a transmitter, and this is a receiver. At the receiver, we have to first estimate the channel parameters based on the PSATS symbols. And after channel is estimated, then we perform signal detection and get the estimated symbol. The whole system design objective to recover the transmitted symbol XK, and here to the receiver we will recover it and to make it more as accurate as possible. This is a traditional channel estimation and signal detection approach. And with machine learning, we can use the neural network to substitute channel estimation and signal detection block. In this neural network, the input consists of 2 parts. One part is corresponding to the received PSATS OFDM block, and another one is the received data block. With the received PSATS OFDM symbol block, the neural network can estimate the channel parameters or channel state information implicitly. Be careful. Here, we're not estimating the channel explicitly, we just estimate it implicitly. And using the received data OFDM data block together with the channel parameters or channel features, which implicitly estimated, this neural network can recover the transmitted symbol. So in brief, the input of this neural network is the 2 OFDM blocks corresponding to the PSATS and corresponding to the data. The output is just to recover the data. The training of that neural network is very direct, and we just use data generated from the simulation, and during the data generation, we generate a channel on a different conditions. Our optimize the model parameter is found to minimize that L2 loss function, and we just use standard gradient approach to find the parameters or weights of the neural network. This figure shows the outstanding performance of the deep learning-based joint channel estimation and signal detection. And let's look at this case. We have 64 pilots. If we have 64 pilots, in that case, channel estimation problem can be formulated as a linear estimation problem. In that case, linear minimum mean square error channel estimation is the best way to deal with it. And in that case, deep learning based approach is very close to the linear minimum mean square approach because it's upper bound. So our deep learning based approach is very close to it. And of course, both machine learning based approach and minimum mean square error approach are much better than the least square approach. And however, if we reduce the number of pilots from 64 to 8, in that case, the original estimation problem cannot be formulated as a linear estimation problem. So the least mean square error approach is not good at all. So in that case, my deep learning based approach has some small performance degradation, but can still work very well. While the other approaches, such as least square approach and the minimum mean square error approach, doesn't work at all. And here, that was our initial work, which demonstrated the power of deep learning for physical layer processing in communication systems. Now let's talk about model-driven deep learning in physical layer communications. So before we talked about in our initial work, we use data-driven method for the channel estimation and the signal detection. Basically, we use a fully connected neural network to perform joint channel estimation and signal detection, and then we use the data to train that neural network, and which usually have lots of parameters to be trained. As a result, it will converge very slowly. And also, the obtained result cannot be explained because we just regard that neural network as a black box. So we cannot do any explanation because it's hard and because it's strongly nonlinear. And with model-driven deep learning, we hope we have a chance to reduce the number of parameters and improve the performance. And this is a general block diagram of model-driven deep learning neural network for communication systems. Basically, be careful, in this block, and we call it a model-based network with parameter W, which means when we design that network, we exploit the expert knowledge and use that one together with machine learning. And we're trying to use machine learning to improve the performance of the system. And we're trying to use expert knowledge to reduce the number of trainable parameters. So in that case, even though the block diagram seems similar or same as the previous one, but inside of this block, the trainable parameter is very small. We have only few parameters to be trained. And also, because the number of the parameters to be trained is small, and in that case, we only need a small data set to train this neural network, and it converges very quick, but the performance improvement is pretty significant. Let's give an example. And this is I just use the MIMO detection as an example. And for the detail, you can see our publication this year. And basically, everybody can understand and can see this is basically MIMO system. And here, X is a transmitted signal vector, and Y is the observation at the receiver, and N is the channel noise. We assume we have estimated the channel matrix accurately here. With observation and with estimated channel matrix, we're trying to figure out, try to estimate or detect what has been transmitted. So traditionally, we have three categories of approach. One of the category is the optimal approach, which is a MAP approach or maximum likelihood detection approach. And it has a very high complexity. And the complexity is exponentially increased with the size of the transmitted symbol vector. And we also have like a no complexity approach, such as zero forcing approach, linear minimum mean square approach. And those approaches are with no complexity, but the performance is pretty poor. There are some approaches that with a complexity not much higher than the linear approach, but the performance is very close to the maximum likelihood approach, the optimal approach. Two of them are called AMP-based detector and an EP-based detector. They have a good performance, but as I said, the complexity is reasonable. And so we're trying to use deep learning for this AMP approach to further improve its performance. This is an approach which is called OAMP. It's orthogonal approximate message passing approach. And we know that AMP approach has been for a while. It's proposed by a professor at Stanford University. And about several years ago, my friend Ping Li and his student, they developed something called orthogonal AMP, which can significantly improve the performance of the AMP approach. And this is an approach called OAMP approach from this paper. And basically, it will use this iterative approach to estimate the transmitted symbol. And this is the approach. We are trying to use the deep learning approach to improve the performance of this system. Basically, we unwrap this approach, and we get this one. This is the first layer corresponding to the first iteration, the Tth layer corresponding to the Tth iteration, and the final layer corresponding to the final iteration. And rather than just directly unwrapping the previous iterative approach, in each iteration or each layer, we put two parameters, two trainable parameters, gamma t and theta t. And so that we can improve the performance. And for example, and if I have 10 layers here, which means I have 10 iterations here, and each iteration will have two parameters, and in total I have 20 parameters for this algorithm. And in that case, we have to train this approach so that to optimize the optimal gamma t and theta t for each iteration. Of course, the relationship between gamma t and theta t and the system feature is very complicated. You can never use the mathematical tool to derive that. But you use machine learning, we can easily train this gamma t and theta t. We just use bunch of neighbor data set to train this algorithm, basically train this gamma t and theta t to get the optimum values for each layer. And this is the performance. And from this figure, we can see the approach can significantly improve the performance. The red one is the original OMP approach. And the blue one is the performance using machine learning to improve the performance. And from here, if we use 16 QAM, our performance improvement is as large as about 3 dB. Of course, if we use other modulation, we can still find performance improvement. For example, if it's like QAM here at the 1% BER, we can have like about a half dB performance improvement. At the 16.4 QAM, we can have about 2 dB performance improvement. Okay, have introduced the initial work which demonstrated the power of machine learning for communication, and also introduced the model-driven deep learning for physical communications. Now let's briefly talk about something called end-to-end wireless communication systems. Okay, as I said before, I use a neural network to represent the transmitter and use another neural network to represent the receiver. Of course, and the channel, we are talking about the wireless channel, which changes according to the environment. And whenever we train these two neural networks, usually we design the system offline. So we don't know what is the channel. Careful. When we design the system, we don't know the channel. This is a critical issue. So we have to find the way to optimize neural network while we don't know the channel. Okay, there are a couple of ways to deal with that. The first way is invented by Alcodia and Hoydes from Bernaps in France. Basically, the receiver neural network is easy to train because we can easily construct the loss function based on the recovered data. And then train this neural network use gradient approach. But the transmitter is hard to do usually. And they invented an approach which used the reinforcement learning to deal with the issue. Basically, they regarded the transmitter neural network as a policy and a source state or transmitted symbol as a state. And we have an agent, and once this agent get a state, get the source state, and the agent will take the action. The action here is the transmitted symbol. And the environment, which includes everything outside of this transmitter, the random unknown channel, and the receiver, and so on. And this is the environment. And then we have a receiver, then we recover the signal. And from the recovered signal accuracy, which is set as the reward of the reinforcement learning and context, and from the reward, the edge in the receiver, then we adjust its policy, which is corresponding to the transmitter neural network. And then once this agent optimized this policy, and the optimum neural network or optimum transmitter parameters is obtained. And once transmitter is optimized, then we fix it, and we adjust. Then we adjust this receiver neural network again. Once this is optimized, I fix it. I go back and optimize this transmitter again, and we do that iteratively. And finally, we can get a joint optimization of the transceiver without knowing the channel parameters. Okay, there are a couple of issues in this this system. One of the first issue is the source data cannot be too long. For example, we can transmit several bits of the symbol, and because if the transmitted data is too long, and this action space is too large. A system is too complicated. It's hard to train, or it's maybe even impossible to train the system. Another issue is that this channel cannot be too complicated. For example, if in the real system we have the frequency selective channel and this one doesn't work. And to address these two issues, we propose a new approach. And in this approach, and we have the couple of improvements. So even though the channel is unknown, we can use the GAN to express the channel as a neural network. In that case, the system has 3 neural networks: transmitted neural network, channel neural network, and receiver neural network. And we can optimize those 3 neural networks iteratively. That is to say, when we optimize one, we fix out the 2. Then we do that iteratively. Finally, we can get a joint optimization of the transmitter neural network and the receiver neural network. And of course, another issue is, and how can we make the system work for the when the length of the data is very long? We found that if we use a fully connected neural network as the transmitter and the receiver, and the system is very hard to train when the source data is got larger. And however, if we substitute the transmitter neural network and the receiver neural network by convolutional neural network, we found that we can easily train the system when the source data is as long as 100 bits. So in brief, we use 2 ways to improve the system. One way is here, we substitute a fully connected neural network by a convolutional network. Another way is we substitute an unknown channel by a neural network, use conditional GAN. Okay, this is the performance of the system. And from this figure, we can see, and when the signal to noise ratio is lower than 10 dB, then end-to-end system is comparable with the traditional state of arts. And however, when the signal to noise ratio is larger than 10 dB, and machine learning based end-to-end system is much better than the traditional approach. I have introduced deep learning for physical layer processing. Now I have like 10 to 12 minutes to do introduce resource allocation, deep learning for resource allocation. And as I said, I will introduce 2 examples. And one example is how can deep learning help system optimization. Okay, we noticed that almost all the problems formulated for resource allocation are mixed integer nonlinear programming approach, which is usually hard. It's hard to address. And also usually for most of the problem like that, we usually use the branch and boundary approach to get the optimal solution. Of course, this is something like exhausting search approach, and the complexity sometimes is too high to tolerate in practical systems. And we can use machine learning approach to reduce the complexity of B&B approach. And for example, this is a traditional device-to-device communication network. In this network, and 2 devices which are close together can communicate to each other as long as it will not interfere to the existing cellular network too much. And actually, we studied this work about 10 years ago, and right now this is has been used in many systems. And this is something like a distributed network, which is different from traditional cellular network. And if we want to optimize the network performance, we can formulate the problem in this way. Of course, it's very complicated. Don't try to read this formula. Just tell you how can we get from this one to a complicated optimization problem. And this is to solve this problem, we usually get a suboptimal no complex solution. And here we're trying to help use machine learning to help reduce the complexity of the B&B approach. In this special problem, we are using imitation learning to accelerate a B&B approach. The rough idea is that for the detail, you can see the paper listed here. And the rough idea is like that. We can, the rough idea is like that. And in the B&B approach, we divided the variable into lots of different small areas. And we noticed that for some certain resource allocation problems on a certain situation, some of the area is with a very small chance to get the maximum or minimum point, or in certain area may have a chance to get a maximum or minimum point, but in other area there is a suboptimal maximum or minimum, which are not far away from that. For those two kind of areas, we can delete them from the branch to save the searching time. And this is a simulation example. We assume in this the first table, and we assume the system have 5 cellular users, and we have 2 pairs of the D2D users, and we only use 50 data to train the system. And in that case, we can get the about 90% of the optimum performance, and we can speed up the B&B by 2.5 times. And the performance is pretty good. And the speed, we reduce the complexity into like a 1/2.5, but we can still get 20% or 90% of the performance. And here we increase the size of the problem, and from K is 5 to 7 to 7. Then the performance is still very good, which means this approach has a very good scalability. And also we train the system for this parameter. For the K is 5, L is 2. And if the system is with other parameters, then the performance is also reasonable, which means this approach is also pretty robust. This example just give us a brief example of how can we use the deep learning to help reduce the complexity of the optimization problem. Actually, machine learning can be directly used for resource allocation. And here is an example. We use the V2X communication as an example. And in this communication system, we have 2 kinds of the links. Well, the first link is vehicular to vehicular system communication, which we use regular cellular network. Another one is one is a vehicular to infrastructure, which we use that regular cellular system. And another one is a vehicular to vehicular network, which we use the D2D communication. And usually V2V communication has a stringent latency and a reliability requirement, but the message is usually very short. Because usually like a V2V communication only transmits the important or emergency message among mobiles, and so it requires very short latency and very high reliability. But on the other hand, vehicular to infrastructure communication and usually have a high data rate, and of course it has like a better channel and so on. And then we're trying to perform resource allocation so that we can take care of both V2I link and V2V link. And we put this problem into a context of the deep reinforcement learning. Basically, and we regard the everything, the environment, and we have an agent is each V2V link, and we have a state, which is we observe the channel state information, interference, location, and so on. With the state, the agent will generate an action. This action including transmission power of the signal and which frequency band should we use. With this action, it will affect the environment. Then we get a new reward. Based on the reward and based on its action, this agent then the adjust its policy, and to take based on the new policy, new action, then we have a new environment again and a new reward again, and by doing this again and again, and we optimize this policy. And then once this policy is optimized, and actually we get the policy for the agent or for the V2V link to choose the transmission frequency band and choose the transmission power based on the environment it's obtained. As I said, the environment or state here is a V2V channel interference and so on. So this is the way how can we use this one to generate a resource allocation policy. And the problem here is how can we design the reward to consider the requirements of the V2I link and the V2V link. And here, this reward consists of three parts. One is the data transmission rate of the cellular or V2I link, and the data transmission rate of the V2V link, and also the delay for the V2V communication. And we can adjust these three parameters, lambda C, lambda D, and lambda P, to adjust the relative importance of this three. And here, we directly consider the latency in our optimization criteria. And if you use the traditional approach, it may be very complicated. It's because it's very hard to get to the mathematical model of the delay and the data transmission rate in reality. So anyway, this figure shows the performance of the system, and this is our deep learning performance of the deep learning based approach, and this is the approach of existing performance of an existing approach, and we get the rate of the V2I link, and from this figure we can see our approach gets the best V2I data rate, and also. And we look at the probability of satisfied V2I link, which means the latency satisfied the requirement. And in this figure we can see, and the deep learning based approach has a very high percentage to satisfy the requirement, but the existing approach or random approach has a poor performance relatively. Of course, in the previous talk, in the previous system, we assume each V2V link to take action independently. In that case, we can see the action, the results of the previous action, their impact to the environment, and we can get the optimum policy. But if all the V2V link take actions at the same time, in that case, the system tends to be multiple agent reinforcement learning problem, which means the problem is the system is not stable at all. And in that case, we can use a joint training and distributed deployment to mitigate this non-stationarity of the system. But we cannot totally, completely mitigate or avoid this issue. For the detail, you can see our publications last year. And also, we also investigated how can we compress the channel information and to be transmitted to the fusion center for the resource allocation. And I'm not going to talk too much about it. For the detail, you can see this paper published about several months ago. And well, let's conclude my talk. And in brief, I talked about several issues. And the first group of the problem is the deep learning for physical layer processing. And we provided and our initial result in the area. And also we talked about how can we use deep learning for resource allocation issues. Actually, there are lots of issues for future researcher. For example, you were talking about the end-to-end wireless communication. We still have the case of the dimensionality issue, especially for the transmitter design. And also, we don't know how much better of the E2E based approach than the traditional method, because the only thing we can do is do the simulation and try and find. We cannot have a formula for that. This is because the machine learning approach is usually very hard to analyze. And also, model-driven approach is a very promising method for the coming generation of communication system. In that case, how can we perform trade-off among various issues: performance, complexity, training efficiency, and so on. And for resource allocation problem, multiple agent deep reinforcement learning is always a problem, because you can never overcome the non-stationarity environments caused by multi-user interaction. But we can try to somehow mitigate this problem. And another idea is, can we use inter-agent communications to mitigate the issue? That is to say, if the multiple agent perform some communication, can we reduce or can we completely avoid this non-stationary problem? This is a very interesting problem for everybody. Okay, that's all for my talk, and thank you. And for any questions, you can send me email, and that's all.
Hello everybody, my name is Lulong. Today, my article is custom suppression in cyclic spectrum estimation based on EMD. Also is Hu Jurong, Lulong, and Li Xujie. We are from Hohai University, Nanjing, Jiangsu, China. If you have any questions, please contact with me by this QQ email. We know it is inevitable to generate cost when calculating the cyclic spectrum estimation of complex electronic magical environment interval singles, aiming at the problem of custom in the minor single suppression in complex electromagnetic environment. This paper presents a method for custom suppression in cyclic spectrum estimation based on Empire mode deposition EMD. The effective information of complex electromagical environment singles is expressed by compression and reconstruction algorithm, and the effective information is decomposed by Empire mode. Results, simulation and impedance show that the proposed method can effectively suppress the cost terms. Introduction, Part 1, Introduction. With the development of communication technology, the distribution of communication-based stations is more and more intensive, and the frequency of communication signals is continuously expanding, which makes the reader more and more interfered by the same frequency communication signals. In case of same frequency, the jamming of communication signals to reader belongs to compression jamming. In the electromagnetic space where the reader works, there are interference signals emitted by adjacent reader or hostile readers. Interface signals of wireless modulation forms, bands, and frequencies are suppressed together to form a dense and complex electromagnetic environment. In the electromagnetic environment of reader, the prior information of wireless reader source is unknown. The transmitting waveform is wireless and forms of interference signals are wireless. The research of high precision spectrum as a method of electromagnetic environment signal is the core of improving reader anti-jamming ability. The mean value, auto-correlation, and other statistics of signal are generally parallel. If the parallel changes with the time, the signal is called a cyclic stationary signal, such as communication, reader, remote sensing, and other signals. The second order cyclic spectrum has a low estimation complexity, faster calculating speed, and strong anti-noise capability, which can transform complex non-linear signals and make them periodic. The second order cyclic spectrum can estimate and define the frequency band of interference signals in the electronic environment of MIMO reader better. In this paper, a spectrum analysis method based on second order cyclic spectrum estimation is studied. It is available to generate cost when calculating the cyclic spectrum estimation of complex electronic environment. interface singles, aiming at the problem of causing in cyclic estimation. These people studied the effect of based on entire model decomposition (EMD) and analyze the performance of algorithm through simulation. Part 2. Cycle spectrum estimation. Data received single can be defined as singles and noise. Noise is a random single with zero mean value, and they are independent of each other. So single can be represented as follows. For Formula 1, the second order hypothesis product of single is calculated and represented as follows. Where tau is the time offset, Qinghao is represented the conjugate. The formula is as follows. RF is the Fourier transform of RT. W is the cycle frequency. T0 is the period. Part 3. Constant suppression on EMD. In order to express a single more concise, the signal is usually transformed into a real basis of frame. When the number of non-zero components is far less than the number of the original singles, this small number of non-zero coefficients can be called the sparse representation of the original singles. Collect the single RT at a point N. Define R as the projection confidence vector of X on the orthogonal basis Y. We can use the orthogonal basis vector to represent complex electromagical environment singles in space. The formulation is as follows. It is difficult to just solve the projection confidence vector A, so it is transformed A pair. That is, therefore, the single is as follows. Empire modeling, the purpose of imagery is to demonstrate the single with poor conversion into a set of in-stream mode function IMF with good performance. The specific steps of EMD are as follows. Step 1. Step 2. Calculate the envelope mean as. Step 3. The components are obtained by the envelope mean from the received singles. Step 4. Whether the formula is as follows. Step 5. The remainder of first order IMF is obtained. Step 6. Repeat step 1 to step 5 with as a new single. When the resident amount of nth order IMF is constant and cannot be further demarcated, the EMD algorithm is complete. The camera diamond improved algorithm is as follows. From start to end. Electronic environment single, sparse representation of single, comparison measurement, reconstruct the single and conduct EMD. The cyclic spectrum of diamond single is obtained and the line is performed. Sorry, this is a mistake. For simulation, in this section, the pattern of single FM and LFM will be selected to simulation the complex electronic environment that the reader works in. The carrier frequency of FM is this. At this time, the single mode of reader ordering complex can be expressed as follows: RT FMT 加 S LMFT 加 NT。Figure 2 shows that a cyclic spectrum is a result of FM and LFM. F is frequency, alpha is the cyclic frequency, S is the cyclic spectrum. Figure 3 shows cyclic spectrum as a result of FM and LFM based on EMD. In order to analyze the cyclic spectrum of FM and LFM more clearly, the second time of cyclic spectrum estimation counter of FM single and LFM single in Figure 1 and Figure 3 are shown as Figure 4 and Figure 5. Like this. Figure 4 shows that the frequency band of jamming single is all kinds of nodes. Compare Figure 5 and Figure 4. The constant in Figure 5 is completely suppressed. As the complexity of single increased, the complexity of cyclic spectrum estimation of single will increase, and the constant will also become complex. The improved cyclic spectrum estimation algorithm not only improves the reliability of cyclic spectrum estimation of complexity electronic magical environment interface singles, but also effectively eliminates the cost terms. Part 5, conclusion. From the simulation, we can get a conclusion that is as follows. This paper proposes cost suppression method for cyclic spectrum estimation based on EMD. The cyclic spectrum of common jamming singles such as FM singles and LFM singles is studied in physically. As the complexity of singles increase, the complexity of cyclic spectrum estimation of singles will increase, and the cost terms will also become more complex. Simulation results show that the proposed method can effectively suppress the cost of multi-single in a complex environment and improve the resolution of self-term. That's all. Thank you.
Hello everyone, it's my pleasure to be here to introduce my work. The topic is MininetE, a lightweight emulator for space information networks. I will introduce my work as follows. At first, let me introduce the background of my research. With the continuous development of space information networks, there is an increasing demand for an appropriate emulation platform to carry out research on space networking. The emulation platform should support not only accurate space-link property modeling, such as dynamic topology, and so on, but also space networking technologies such as DTM and SDM. The currently available network testing techniques have their pros and cons. Testbeds give researchers the ability to get the most credible testing results, but meanwhile, they are too expensive. Simulators such as OPNet and NS3 use discrete events to simulate network events. They are lowest cost, but they lack realism. They cannot generate real data flow among the network. In contrast to simulators, emulators run real protocols and network applications on each virtual node, so they can generate real data flow. Compared with testbed and simulation, emulation is relatively high fidelity and low overhead. Therefore, we choose MininetE, an open-source emulator, and then we extend MininetE to meet our requirements for space network emulation. Firstly, we add support for space networking technologies, such as DTM, and then we implement more accurate space-link property modeling, including intermittent links and dynamic topology. Next, I will introduce the implementation of our scheme. Firstly, let's get an overview of MininetE. MininetE is a widely used lightweight emulator when it comes to terrestrial network emulation. It's based on Linux namespace virtualization technology. Besides, MininetE provides extensible API to customize network topology and support for OpenFlow and SDM. As shown in Figure 1, a basic MininetE network consists of host, link, switch, and controller. Unfortunately, we found that MininetE lacks the necessary namespace isolation to support space networking technologies, such as DTM, which is necessary to emulate space information network. Therefore, our first step in the implementation of MininetE is to add additional namespace isolation. Apart from the namespace isolation provided by MininetE, including network namespace and mode namespace, MininetE adds support for isolation of the UTS namespace, IPC namespace, and the PID namespace. After the work is done, we run I1 DTM in both MininetE and MininetE. The result is illustrated in Figure 2. Within MininetE, after the first instance of I1 is started in the host 1, host 2 fails in starting another I1 instance. On contrary, MininetE run I1 successfully in both host 1 and host 2. After this, in order to implement dynamic topology in space network, we decide to use a centralized emulation architecture with SDM controller, as shown in Figure 3. Firstly, all virtual hosts are connected with an open vSwitch to form a star topology. Then, The SDN controller controls link up and down between hosts by controlling the flow table of the switch. The control flow is shown in Figure 4. At first, we stack link flow table, and then we use timers to set a dynamic link flow table. So far, we have completed the MininetE. The next part, I will introduce experiment results and the discussion. In order to evaluate the reliability of MininetE, we reproduce a detailed experiment presented in Paper 1 with MininetE. The topology of this scenario is shown in Figure 5. It consists of 4 detailed nodes: a moon lander, a moon satellite, a terrestrial gateway station, and a mission control center. Note that intermittent space links are denoted by dotted lines, and the terrestrial wired links are denoted by continuous lines. The content plane and the link characteristics are summarized in Table 3. Note that the links between Moon and the Earth have a propagation delay of 1.3 seconds, while the delay of our links is negligible. In the scenario summarized above, we transfer 10 bundles of 50 kilobytes from the Moon lander to the Mission Control Center. Figure 6 presents a comparison between some results presented in Paper 1 and those obtained with the MininetE. Obviously, these two results almost coincide, which proves that MininetE is capable of testing DDN networks. The last part of my presentation, there are some conclusions and prospects. Firstly, with additionally namespace isolation, MininetE supports space networking technologies, including DTN. Secondly, with the method of dynamic topology control, MininetE can emulate space network with more accurate link characteristics. Lastly, emulation results prove that MininetE is capable of testing DTN networks. In the future, more experiments will be performed to prove that MininetE can meet requirements of emulating more networking techniques and more complex network topology. That's all of my presentation. Thanks for your attention.
Hello, ladies and gentlemen. It's my honor to be here to introduce my work. The topic is on the performance of packet layer coding for delay-tolerant data streaming in DeepSpace. I will introduce my work as follows. At first, let me introduce the background of our research. As an increasing number of managed space programs will be undertaken in the future, multimedia services in deep space such as real-time videos are becoming more and more important. However, the space link displays special features such as larger link delay, higher bit error rates, bursts of errors, and packet deloading. As we know, in order delivery and real-time are critical points in data streaming propagation, so it is difficult to perform high-quality data streaming service in deep space. To get over these problems, bundle stream service, which is known as BSS, has been proposed. This picture shows the stack of BSS. BSS conducts the streaming functions at the bundle layer and provides two transport services below the BSS forward, including best effort service and reliable service. First of all, when the data is sent for the first time, it will be transmitted through the best effort service by UDP or green LTP to ensure that the data is sent to the receiving side as soon as possible. During the communication process, if some packets are lost, the reliable service will retransmit the lost packets by TCP or red LTP to ensure that the reliability of transmission. Besides BSS, a new space streaming transmission scheme called RTP over DTN was proposed by CCSDS, which can ensure higher quality of video transmission in deep space. RTP provides a lightweight packet format for the transmission of media-related payloads. RTP is designed around a fixed 12 bytes header, along with the header extension field, as can be seen in Figure 2. In order to make it apply to deep space, RTP should be implemented over bundle protocol. RTP may be encapsulated into DTN bundles with minimal modification, instead treating the entirety of the RTP packet as a single bundle. Considering RTP packets have arbitrary sizes, so it can be concatenated, and the following rules should be followed. Concatenated packets must have the same MAC value. If the MAC value changes, a new bundle should be studied. All RTP payloads in a concatenated bundle must belong to the same media stream and have the same time step. After the first RTP package, all headers can be stripped. This picture shows an example of a concatenated RTP bundle. However, due to the bad transmission conditions in deep space, BSS or RTP over DTN may not perform well on real-time data delivery service. There are some challenges. Firstly, the high loss rate of data in deep space may deteriorate the quality of real-time stream data delivery. And secondly, due to the long propagation time in deep space, retransmission is an expensive approach to guarantee the reliability. So, we propose a new scheme, integrating the packet layer coding into the BSS or RTP over DTN to improve the quality of space stream service. Next, I will introduce the design of our scheme. The design of packet layer coding for space streaming has been shown in Figure 4. Note that LDPC code is performed at the bundle layer. Because we believe implementing the FEC codes at the up layer has stronger error correction abilities by packet layer coding. This picture shows the encoding and decoding flow of our scheme. Firstly, several bundles converge into a data block. Then, each data block would be cut into K LTP segments. The K LTP segments are sent to the LDPC encoding process. The encoding process includes the following steps. Step A. Matrix filling. K LDP segments are passed to encoding process. They are written as rows of an n-row matrix. B. Matrix encoding. M redundancy symbols are added into the last m rows of the matrix. Step C. Matrix passing. The n rows are passed one by one to lower layers. On the receive side, the decoding process includes the following steps. A. Matrix filling. Let L be the number of packets lost and the other packets have arrived. Their payload is read and return in a matrix B, matrix coding. To have a success, it is necessary to receive at least k of the n symbols transmitted, whatever they are. C. Matrix passing. The first k rows of the matrix are read and passed one by one to the up layer. Next, I will introduce experimental results and discussion. To implement a deep space delivery environment, 3 computers were deployed to set up the experiment. The node 1 is the source node and node 2 is the end node, and the last computer is used as a channel emulator. It can control the changes of channel error rates and propagation delays. The experimental factors and configuration have been shown in the table. To evaluate the performance of packet layer coding, the following metrics are used. First is the stream delivery time, SDT, which is the duration for all the data to be successfully delivered to the receiver. And the second is the end user's display efficiency, EDE, which is the ratio of displayed frames to all transmitted frames within the initial transmission. A shows the effect of propagation delay on SDT at the same channel bit error rates. According to the results, BSS with LDPC performs better than the original BSS in different propagation delay, which means no matter how long the delay is, BSS with LDPC can deliver all the data in a short time. B shows the results at different channel bit error rates. When the delay is 1 second, the BSS with LDPC can deliver all the data in 30 seconds even in bad channel conditions, while original BSS takes more time. The next 2 pictures shows the comparison between BSS and LDPC BSS based on EDE. It is apparent that BSS with LDPC can display more stream data in the receiver than original BSS. The performance on packet layer coding for RTP over DTN is focused on the number of lost packets respect to propagation delay and BER. Table 2, Table 3 shows the number of lost packets within the transmission by RTP over DTN with LDPC and RTP over DTN without LDPC. It is apparent that RTP over DTN with packet layer coding can provide higher quality service by reducing the number of lost packets. Next is the last part of my presentation. Based on the emulations in this work, we evaluated the contribution of packet layer coding to streaming data delivery for future deep space applications. And the results of the experiment strongly prove that space streaming with packet layer coding has great advantages for the original space streaming service, no matter in terms of BSS or RTP over DTN. When packet layer coding is applied in BSS, the proposed LDPC BSS scheme achieves better performance in terms of the SDT and the EDE. And when the packet layer coding is applied in the RTP over DTN, the proposed LDPC RTP over DTN scheme achieves better performance in terms of the number of lost packets. So, benefited from stronger error correction abilities, packet layer coding ensures the reliability of stream data delivery and improves the quality of stream service. That's all of my presentation. Thanks for your attention.
Good morning, everyone. I am Chen Xibian from Jiangsu University. Today, I am going to introduce the adaptive particle swarm optimization for harmonic impedance matching in 5th generation power amplifier design. First, I will introduce the background and motivation of this work. Second, the adaptive particle swarm optimization will be briefly introduced, followed by the design and optimization of the matching network. Then, the optimized power amplifier will be simulated and verified. Finally, a conclusion will be given. Nowadays, as the mobile communication system develops into the 5th generation era, devices with communication capabilities are being used on a large scale. Therefore, a large amount of energy is consumed in the communication system, and this consumption continues to increase. In the mobile communication system, the power amplifier is an indispensable part, and the energy consumed by this model occupies a large part of the communication system. Therefore, one of the key indicators of power amplifier is efficiency. In the process of designing a power amplifier, higher efficiency is an indispensable requirement. In the power amplifier circuit, the existence of harmonics is the key factor affecting its efficiency. So there is a way to control the impedance of harmonic loads to improve the efficiency of the power amplifier. Class F power amplifier is proposed to obtain high efficiency by controlling harmonic load impedance. The impedance requirement of the power amplifier is shown in the equation. For the voltage waveform, in order to obtain a square wave close to the ideal, the odd harmonic impedance must be in short circuit state, except for the fundamental wave. For the current waveform, in order to obtain a half-sine waveform, the even-numbered harmonics need to be in open circuit state. After satisfying the above impedance requirements, the ideal class F power amplifier voltage and current waveforms can be obtained. Because the voltage and current waveforms do not overlap, the power loss of the amplifier is reduced. This method can improve the efficiency of the power amplifier. Although there are multiple technologies used in the design of high-efficiency power amplifier, it is necessary to use more excellent optimization to design and optimize the matching network of power amplifier, makes the power amplifier achieve higher efficiency. The combination of the optimization and the design of power amplifier can achieve satisfactory results. First, according to the design requirements of the power amplifier, determine the matching network structure that needs to be optimized and set the optimization goal. Then, use the algorithm to optimize the design. Before we design and optimize the matching network, the theory of adaptive particle swarm optimization will be introduced. The basic concept of particle swarm optimization is derived from the study of the foraging behavior of birds. The flowchart of the algorithm is shown in the figure. In particle swarm optimization, the solution of each optimization problem is a bird in the search space. We call it particles. All particles have a fitness value determined by the optimized function. and each particle also has a speed that determines the direction and distance of their flight. Then the particle follow the current optimal particle and search in the solution space. A kind of particle is used to simulate individual birds. Each particle can be regarded as a search individual in the n-dimensional search space. The current position of the particle is the candidate solution of the corresponding optimization problem. The flight process of the particle is the search of the individual process. The optimal solution searched by each particle individually is called individual extreme value, and the best extreme value in the particle swarm is the current global optimal solution. The particle swarm is constantly iterating, updating the speed and position. Finally, the optimal solution that satisfies the termination condition is obtained. In order to balance the global search ability and the local improvement ability of the particle swarm optimization, a nonlinear dynamic inertial weight coefficient formula can be given as follows. The equation of omega is called adaptive weight because the inertial weight changes automatically with the target function value of the particles. This is the key of the adaptive particle swarm optimization. In the third part, a method used to optimize the design of matching network is proposed. The first is the design and optimization of the input matching network. The target source impedance of the warp speed transistor at 3.5 GHz can be determined by using sourceful simulation in Keysight's advanced design system. According to the design requirements of the exercise method, select the L-shaped network structure, as shown in the figure. In the definite structure, Z1, Z2, Z1, Z2 are the four optimized parameters. According to the impedance transformation formula of transmission line, ZS1 can be obtained. Similarly, the impedance Z open of the open transmission line can be calculated, and it can be obtained from the circuit schematic in figure that ZS is the parallel connection of the ZS1 and Z open, so the expression of ZS is derived. According to the previous impedance results and the formula, the equation of F can be obtained. This is the evaluation function for this optimization. In the optimization, the population size is 10 individuals, and the evolutionary generation is 60 generations. In order to observe the change trends of fitness, the optimization program was run 10 times, and the results are shown in these figures. Figure A shows the relationship between the value of the objective function and the evaluation generation during optimization operation. It can be seen from Figure A that the blue line in the figure represents the fitness value of the best individual, and the red dotted line represents the average fitness value optimized 10 times. As the number of the iteration increases, the fitness value of the best individual keeps decreasing from around 1 and finally stabilizes at around 0. And the average fitness value also shows a downward trend, which is stable at around 0 between 30 and 40 generations. Figure B and Figure C give the changes of various parameters in the optimal optimization. The result shows that these parameters are divided greatly from the expected value in the earlier stage. But with the increase of the number of the iterations, they quickly turned to optimal value. The fitness data is close to zero, indicating that the difference between the current impedance and the target impedance can be minimized, which means that the input matching network is optimized. Then there is the design and optimization of the output matching network. According to the impedance transformation formula of transmission line, Z01 can be calculated, and according to the equation of Z01, Z02 can be expressed. Similarly, the impedance of the open line Z01, Z02 can be obtained. Next, the equation of the Z03, Z04, Z05, and 0 can be inferred step by step through a method similar to the input matching network. Finally, according to the target's fundamental second harmonic and third harmonic impedance values, combined with the equation of the 0, 3 evaluation functions are obtained, except for the increase, the optimization variables and different evaluation functions. Other optimization settings of the output matching network are the same as the above mentioned input matching network. After the impedance at 3 frequencies is used as the optimization target, the optimization output results are shown in figure. Because the increase of the optimization variables and objective functions, the optimization results do not reach 0, but the fitness value of the 1.6 is also close to the target. The fourth part is to design and simulate the optimized matching network with advanced design system. After using the above-mentioned adaptive particle swarm optimization to design the input and output matching network, the power amplifier can be designed and simulated in advanced design system. The simulated gain and efficiency versus output power are shown in figure. It can be seen from the results that the saturation power of the amplifier is about 42 dBm and 3.5 kHz, and the maximum efficiency reaches 75%, reaching a higher power and efficiency level. The results verify the feasibility of the proposed method. Finally, a conclusion will be given. At last, we will give the conclusion. First, an optimization design method is proposed to improve the efficiency of power amplifier. Then, a 3.5 kHz power amplifier is designed for verification. The result shows that high efficiency can be achieved at this frequency by employing the proposed method. Thank you for your attention.
Ladies and gentlemen, my name is Xinting Wang. Today, I am honored and proud to have the opportunity to speak at this meeting. We are going to discuss a new method to construct non-binary QC-LDPC codes based on ACE value. speech is divided into 5 parts. Firstly, allow me to introduce the research background and significance. Communication has been one of the deepest needs of the human race throughout recorded history. It is essential to forming social unions, to educating the young, and to expressing a myriad of emotions and needs. Good communications is central to a civilized society. In the communication system, the information sent by the source enters the channel through the source encoding and the channel encoding, and is received by the receiver through the reverse operation. The main function of channel coding is to improve the accuracy of receiving information by adding extra check information. LDPC codes are a type of linear block codes. The excellent error correction performance and efficient parallel decoding strategy make it commonly used in communication, particularly compared to binary LDPC codes. Non-binary LDPC codes has stronger ability to resist burst error, to achieve higher error correcting performance and transmission rate, which has been used in new satellite navigation system and so on. Here, I enumerate the advantages and disadvantages of non-binary LDPC code. The advantages of non-binary LDPC codes are stronger ability to resist burst error, various code rate, efficient parallel decoding strategy. And the disadvantages of non-binary LDPC codes are poor performance in medium and short code length, complex structure process, high decoding complexity. At present, papers mainly focus on the construction of binary LDPC codes, and the research on non-binary LDPC codes are relatively few. Here, I am going to briefly introduce the existing construction methods. Similar to binary LDPC code, non-binary LDPC code can also be divided into 2 categories. One is a kind of random structure LDPC code, which follows some rules and is obtained by computer through a large number of calculations, such as PEG algorithm, ACE algorithm. A class of structured LDPC codes using algebra or combined tools such as finite field operations, finite geometry operations, and matrix operation like masking. More attention are placed on the construction of non-binary quasi-cyclic LDPC codes. Its QC feature greatly reduced the complexity of coding and decoding. The following indicators could distinguish a good parity check matrix of a LDPC code: the degree distribution, the cycle distribution, the trapping set, the stopping set. The shortest cycle is called girth. Generally speaking, larger girth of a parity check matrix is a common way to improve error correction performance. Since cycles with the same length should not be treated equally, cycles can be distinguished according to their connectivity. Therefore, combined with the structural construction, This paper proposes a construction method based on ACE value that considers both the number and the connectivity of cycle. We are going to talk about what is a non-binary quasi-cyclic LDPC codes. First of all, we can see it from Formula 1. The parity check matrix H is an NBQC LDPC code, consists of a base matrix B and the circulant permutation matrices CPM. All elements in B belong to a finite field. For any positive integer R, let Q be an R multiple R, a circulant matrix over a finite field GFQ, with columns and rows labeled from 0 to R-1. The top row contains a single non-zero component, a non-zero element in a finite field at the certain location J between 0 and R-1. Each row in Q is the cyclic shift of the row above it one place to the right, and the top row is the cyclic shift of the last row of Q one place to the right. There are two types of Q. Suppose a finite field GF4 R equals to 3. Different position but same element in each row of a Q array CPM. As for alpha multiple CPM, different in both. In this paper, let's take the Q array CPMs for example. Part 4. Construction method based on ACE value. The cycle in a parity check matrix is an important factor affecting the performance of QC-LDPC codes, particularly length of 4. However, cycles with different lengths may have different effects on performance. Not only the number of short cycles, but also the connectivity of cycles plays an important role. Remaining cycles with high connectivity rather than reducing short cycles for increasing errors blindly could improve error flow effectively. The masking algorithm is presented to distinguish and select more harmful cycles to make a better cycle condition. The definition of ACE value can be seen from Formula 2. The sum of original degrees in a cycle is called the ACE value of a cycle. The flowchart of the entire masking process is shown at Figure 1, in which the red box represents the innovation in this paper. After we have gotten the base matrix B, the next step is masking it for the better cycle distribution, that eta as a ratio. Search the number of cycle G and build a cycle distribution matrix D. If there is only one maximum in D, turn the element in this position to 0 and calculate the number of cycle G of the new base matrix B. If not, randomly choose one position. The masked matrix may not be optimal. With some improvements, the entire masking process becomes to Figure 2. Masking a position means all cycles related to it are removed and the ACE value of cycles that the other positions in the same row or same column participated in are decreasing. Therefore, it is crucial to choose a rational place If there is only one maximum in D, turn the element in this position to 0 and calculate the number of cycle G of the new base matrix B. If not, we need to consider the ACE value of cycle G star to get a base matrix with larger ACE average value. We model the above selection process into Formula 3. Part is simulation resources and analysis. From Table 1, the girth of B1 over a finite field 16 is at least 6. It has the number of cycles of length 8 is 180, with its average value is 6.167. B2 over a finite field 16 is constructed for corporation, whose tenor graph has girth at least 10. In reference 8, a class of LDPC codes proposed by using different combinations of the cyclotomic cosets in a finite field performed better than some EG-LDPC codes. The code word in 8 has girth at least 6, and the number of cycles of length 8 is 150, with its average value is 1.8. It could be seen that under a finite field 64, although the number of cycle 8 in B3 has increased, the ACE average value is higher. B4 is constructed for corporation, whose tenor graph has girth at least 10. In reference 5, a very large class of QArray CPM QC-LDPC codes were constructed beside on two arbitrary subsets of a finite field. As for 5, it has some cycle 6 with its average value is 3.25. It could be seen that those methods in this paper make a reasonable compromise between the number and the connectivity of cycles. The two pictures show the NBQC-LDPC code under larger ACE values had better performance than those who have larger girths. Compared to other construction methods, the new masking methods proposed by this paper had advantage in performance. Meanwhile, NBQ-LDPC codes have stronger error correction capability than binary LDPC codes. In this paper, we presented a simple and flexible masking method for constructing irregular NBQC-LDPC codes. The proposed methods aimed to ensure the left cycles in a mask-based matrix have larger ACE average value under the constraints of the number. Examples in different range of lines and finite fields were presented to illustrate the advantages of this feature. Simulation results show that the codes constructed in this paper have better error performance. Thank you for your careful listening.
Today I'm going to talk to you about our paper, a local high-capacity LEO satellite constellation design based on an import NSGA-II algorithm. My presentation is divided into 4 parts. Part 1 is introduction. We all know satellite communication has the advantages of wide coverage, large communication capacity, compared to terrestrial communication, and it is not easily affected by geographic nature deficits. But the coverage of one satellite is limited, so we often need a constellation satellite communication system composed of multiple satellites to communication. Also, the cost of satellites is relatively high, and the satellite constellation usually needs to consider both cost and communication performance. How to use the least cost to achieve best communication performance? We should need a trade-off. We concentrate a design multi-objection optimization model of satellite constellation for local high capacity, using the import NSGA-II algorithm to solve model, using STK software to simulate the results of the solution. Various constellation design schemes have been proposed in different countries, and some constellation satellite communication systems have also been established. The primary commercial constellation satellite communication systems built and operated are BeiDou, Globalstar, OneWeb System, Starlink. Here, we mainly compiled with Globalstar, and we consider the local high-capacity satellite constellation design. The design and optimization of the constellation satellite for the local high-capacity LEO satellite communication system are aimed at reducing the development cost of the satellite constellation and building a more convenient and economical satellite communication system. We choose China as the target area. In the design and optimization purpose of the constellation design is closely combined with the real needs of users. Under the two conditions of communication quality and cost efficiency, giving a feasible constellation deployment solution for a local high-capacity satellite communication system. In the optimized design, we choose the Walker constellation as the basic configuration. Continue to optimize the number of satellites, the number of orbits, satellite orbits period, orbits angle, and the other parameters. We will describe the issue in detail in the later section. Part 2. System Model. According to the previous discussion, we need to achieve a trade-off between the performance and the cost of the constellation. It can generally be modeled as a multi-objective optimization problem, assuming that there are 3 optimization goals, and these 4 optimization goals may conflict with each other. The mathematical model can usually be expressed by the following formula. Cost is our cost target. C total is our performance target. Represents the total communication capacity of the target area, and C represents the average coverage of the Constellation communication system. The specific meaning of these parameters can be found in our paper. Our system model. We have 4 parameters are NP, Nsite, P, theta. The specific meaning of these parameters can be found in our paper. First of all, the population of the target area can be calculated by the density of the ground population and the population distribution. In this model, the actual population mainly refers to the statistic results of NASA's International Earth Science Center based on the relevant information on the website. The population density of the ground can be calculated. We use population density data for 2020. See the figure 1. The size of each pixel in this picture represents population density data. There are also some parameters data which are based on some literature. To ensure the cost of constellation design, the total number of constellation satellites is limited to 100. The number of orbits doesn't exceed time, and the number of satellites in each orbit during exact time. Besides, the inclination angle range of the track is limited to 30 degrees to 60 degrees. Part 3 is algorithm. In our algorithm, the flowchart of satellite constellation optimization is as the figure. We use the improved NSGA-II algorithm to solve the model. We use the improved NSGA-II algorithm to solve the model. According to the proposed optimization scheme, the improved NSGA-II algorithm is used to solve the satellite constellation design of the target area. The results as follows. The satellite constellation uses the Walker constellation as the basic configuration and consists of 35 low orbit satellites with a total of 5 orbit inclination angles. It is a 48-degree orbit plane, and there are 7 evenly distributed satellites in each orbit, with a satellite orbit period of 110 minutes. The constellation illustrations simulated by STK software are shown in Figure 3 and Figure 4. This is my presentation of 4 parts. Conclusion. To verify the effectiveness of the new satellite constellation scheme given for the target area in this paper, we manually compile it with global star system. First of all, we use the STK coverage analyze module to analyze coverage rate, and use our design and global star to calculate coverage rate for the same area. The results are shown in Figure 5 and Figure 6. The figure rate of our design is more concentrated in 100%, which shows the that the solution is more stable than Globestar, than the cost analysis. In our design, there is only 35 satellites, and the Globestar have 48 satellites. In terms of space segment development cost, the overall cost of the constellation we design is lower than Globestar, which just means the design goals of this paper and greatly saves constellation development costs. In our work, the constellation design problem for the target area is proposed in order to achieve a composed between cost and performance of satellites. The paper constructs a design multi-objective optimization model of satellite constellation and used the improved NSGA-II algorithm to save model using SPK software to simulate the results of the solution. But we should be more innovative. Our solution just compile the design with Globestar. Comparing the design with Globestar, we can see that our solution is better than Globestar in terms of coverage, performance, and cost. In addition, due to some shortcomings in our design scheme, such as not considering the impact of inter-satellite links, not considering the growth costs, we will improve it in future work. Thanks for your listening. This is my overall presentation. Thanks.
Today, I will make a presentation about bundles aggregation of Licklider transmission protocol over lossy and highly asymmetric space network channels. This is my outline of the presentation. Background: bundles aggregation of Licklider transmission protocol. Analytical modeling, model validation and numerical results, summary and conclusions. Licklider transmission protocol was developed to provide reliable and highly efficient data delivery over unreliable space network channels. The LTP aggregation mechanism is studied with focus on its characterization and performance over lossy and highly asymmetric space channels. This figure shows a scenario of LTP data transmission illustrating the effect of CP loss on block transmission over lossy and highly asymmetric channels. In the light of the earlier discussions, a high LTP block transmission data loss rate resulting from a lossy space channel is expected to reduce the RS waiting time and the transmission round-trip time. As a result, it is expected to improve the transmission performance of LTP over links characterized by extremely asymmetric data rates. This part is analytical modeling. The total length of the encapsulated LTP block at the link layer, termed L block link, was formulated as a function of the number of bundles to be aggregated and the fragmented segment size. The total length of the frame overhead, L frame head, is actually the total encapsulation overhead starting from the LTP layer until the link layer. Therefore, it can be simply formulated as a sum of the length of individual head added at layer 1, the link layer, up to the LTP layer. Let TRS be the average transmission time of an RS out of the total number of RSs. As discussed, an RS can only be triggered by a successfully delivered CP segment. In other words, the CP segments that are lost or corrupt when received at the receiver do not generate the RSs. Therefore, TRS can be formulated as follows. Then, denote T block as the average transmission time of a single block out of total number of blocks for the entire file transmission. Let R data be the data channel rate available for downloading data from a deep space craft, Moonlander or Marslander. Then, T block can be formulated as follows. In order to avoid RS transmission delay due to channel rate asymmetry, the average transmission time of a block must be greater than or equal to the average transmission time of an RS sent by the data receiver. So, L block link can be formulated as follows. Therefore, N bundle can be written as a function of other factors, and it is shown as follows. Therefore, the threshold numerical value of N bundle is actually a minimum number of aggregated bundles to be able to avoid the delay of RS transmission. Denote this minimum number of bundles as N bundle minimum. This part is model validation or numerical results. This is a block diagram of the built PC-based test bed. This figure presents compression of the RTT length measured for the first and the last block transmission runs of LTP in transmitting a 1 trillion byte file over an emulated cislunar space communication infrastructure with highly asymmetric channel rates and different channel qualities, and LTP configured with 5 block bundles a block. We can conclude that the only delay effect contributing to RTT loss is the delay in RS transmission, which is caused by the channel rate asymmetry. It is also observed that, along with the channel BER increase, there is a slight decrease of RTT loss. Figure 3 presents TSG illustrating the LTP transmission at packet level at the sending node for delivery of a 1 trillion byte file over a highly lossy cislunar channel with highly asymmetric channel rates and the LTP configured with 5 bundles a block. In contrast to the original RS transmission line, these 4 retransmission lines are parallel, which indicates that there is no RS delay experienced in transmitting them. This can be observed from the fact that the RS lines are becoming sparser along with the transmission because of decrease in the number of RSs sent. Figure 4 shows a zoomed-in view of a selection portion of the TSG in Figure 3, illustrating transmission of 2 LTP data blocks of a file, Block 1 having a CP loss and Block 2 having a regular segment loss. It is observed that the RS for Block 2 is received around 10 sec, while it is unexpected not received for Block 1. This is an indication that Block 2 experiences regular data corruption or loss, not CP loss, due to the high channel rate, and the situation for Block 1 is different. Figure 5 presents the comparison of the RTT length measured for the first and the last block transmission round of LTP configured with 30 bundles a block. The RTT length for the last block transmission round remains unchanged compared to the ones measured for the first block and all other blocks. As a result, the delay effect is resolved significantly, but not entirely. In other words, there is still some delay effect experienced for many blocks. The resulting minor delay effects are accumulated toward the last block transmission. And the last figure shows the TSG for the same transmission of a 1 trillion byte file as the one presented in Figure 3, but figured with a much larger number of bundles aggregated within block, 33 bundles a block. It is expected that a transmission with 33 bundle block resolved roughly the delay of RS transmission and thus leads to an equal length of the RTT for all the block transmission rounds. And the last part is summary or conclusions. In this article, an analytical model is presented for the minimum number of BP bundles to be aggregated within an LTP block for transmission of a lossy channel so that the RS transmission delay imposed by highly asymmetric channel rates can be resolved. It is concluded that, regardless of the number of bundles aggregated within block, along with the increase of channel loss rate, there is slight decrease of RTT. This is because with a high loss rate involved, both the number of CP segments that are successfully delivered to the receiver and the number of RS segments generated in response decrease. The decrease of the number of RS segments leads to a shorter waiting time of RS segments for their transmission, and thus a shorter RTT for all the block transmission runs. On the other hand, regardless of channel loss rate, along with the increase of the number of aggregated bundles, the RTT for all the block transmission runs also decrease because of the reduced number of the data blocks or CP segments originally sent by the output. In both cases of the RTT decrease, the transmission leads to shorter file delivery time and thus increase of output. The performance keeps improving along with the increase of a block size until the number of aggregated bundles are as many as around a threshold number, which is the minimum number of aggregated bundles calculated from the model. The above are all my reports. Thank you.
Mr. Chairman, honorable guests, ladies and gentlemen, good morning. I'm so honored to have the opportunity to speak at EAI WiSATS 2020 online conference. Of course, I'd love to be with you to communicate academic questions and ideas after my speech. Today, I would like to represent my paper Modulation Recognition based on neural network ensembles. My presentation will cover the following aspects: introduction, features, extraction, model of this result analysis conclusions. In this part of the report, I'm going to begin with the introduction of my paper. Okay, what's the modulation recognition? Modulation recognition as an intermediate process between signal detection and demodulation is therefore attracting attentions. The modulation recognition system essentially consists of 3 steps: signal reprocessing, feature extraction, and selection of modulation algorithms. How's the importance of modulation recognition? Nowadays, communication is the primary way for humans contact to obtain information. Modulation formats are various and sophisticated, no matter whether they are communication countermeasures and electronic warfare in the military or mobile communication in public life. What the methods and state of arts of existing papers? There are 2 general classes of the recognition algorithms: likelihood-based and feature-based. Maximum likelihood estimation hypothesis test based on decision series and pattern recognition based on feature extraction. There's nothing with perfection in the world, especially in scientific researches. So there are always more or less different flaws in the existing articles, such as the less accuracy and low SNR, slow convergence of the algorithms, and complex calculation and application. So we make it sense. The pursuit of better makes us study deeply. We dig into research on the above issues, and the approach offered performs well in excellent accuracy of the recognition, simple feature extraction, and small calculation. The contribution of my paper is as follows. We developed a new model of BP of neural networks Ensembles by a combination of the BP neural networks, less calculations, and it's available to apply. The model presented is trained by a data set of the novel and simple feature extraction of my paper. The model performance assessed by the testing set is impressive, delivers high accuracy than the state of the art. Part 2. This section is about the feature extraction. First is cumulative of a random variable. We suppose x is a continuous random variable. The case order cumulative of x is defined as this formula, where the phi omega and the phi omega are density function and engine function respectively. For state externally complex random sequence xn. The moment and cumulate are defined as these two formulas. In my paper, we exploited the second, fourth, and the sixth order cumulates. These are their calculation formulas. Of course, they have you the following advantages. The high order cumulate is always zero for color Gauss noise, means it's less affected by Gauss background noises, so it can be extracted non-Gauss signals in colored Gauss noises. The high order cumulate contains system information, so it can be utilized for minimized phase recognition. Third, it can detect the non-linear signal characters or recognize non-linear systems. Considering that the high-order cumulates will be affected by many factors such as signal amplitude and reference phase, besides the cumulate of the below the second order Gauss noise is not zero. This paper constructs the characteristic parameters are as follows. We use the second order cumulants, fourth order cumulants, and sixth order cumulants. The parameter 1 is Fe as this formula, F2, F3. This part, I will introduce our model for modulation recognition. Because a neural network has some flows, such as first, the number of hidden layer nodes in a neural network will increase greatly all complex modulation signals, which will lead to training difficulty and on account of the difficulties of parameter setting and then fast multiplications of training time. Second, a neural network will cause overfitting phenomenon due to excessive pursuit of training accuracy. Third, the defects of weak roboticness and generalization in a neural network it performs significant difference in prediction of unknown data, which cannot guarantee the accuracy of modulation recognition of the digital communications signals. Thus, we propose the BPNNE model. The BPNNE consists of BP neural network and the neural network ensembles. The picture is BPNNE structure. It contains S ensembles and one ensemble. The SE ensembles indicate the first ensemble. One ensemble manifests the last ensemble. This is algorithm flows. Step 1 is inputs. Step 2 is about divided the input data sets into a training set and the testing set according to the proposition, and divide the training set into T groups randomly and equally. Step 3, according to the training data, the optimal neural network are trained independently by changing the number of hidden layers nodes. Step 4. Weight optimization according to the quantum immune algorithm. Step 5. The output of the secondary neural network ensemble is combined by a simple algorithm. Okay, part 4. This part is about results analysis. The left figure is accuracy covers of the 10 modulation formats under different SNR of BPNNE. From the picture, we can see the accuracy is over 94%, whereas NR is 5 dB. The BPN can recognize 10 modulated signals infallibly, whereas NR is 8 dB during the simple set of my paper. This picture depicts the recognition accuracy covers of 10 modulation formats with different hidden layers nodes of optical BP neural network, whereas NR is 515 dB. We can from the picture we can see the when the node is over 10, the property of the correct recognition is not improved anymore. Okay, the third figure is the performance covers of different methods. So we can, from the picture, we can see our model BPNNE is best of these methods, and our model is 2 dB better than SVM and the single neural network. The last picture is the recognition accuracy in in the picture is mainly used to characterize the generalization performance of the BPNNE model. It can be seen from the picture that MSE coverages to 0.01 when epoch is 70. Which indicates that the generalization either of the model can reach 0.01, showing good generalization ability. Part 5. Conclusions. Okay, in my paper, a method of modulation recognition based on neural network ensembles is proposed on the foundation of the BP neural network. The characteristic parameters are simulated and verified by BP neural network ensembles. The experimental results manifest 10 modulation formats are defined efficiently, including the complex modulation signals such as OFDM and CPM. The algorithm represented has high accuracy, and the extracting feature are simple, which is not complicated for engineering application. Okay, ladies and gentlemen, it has been my pleasure to give you my viewpoints on modulation recognition based on neural network ensembles. Thank you very much for your kind attention. Thanks.
Mr. Chairman, ladies and gentlemen, I'm honored and proud to have the opportunity to speak at this conference. Today, I would like to present my paper, Ground Station Set Selection with Real Cloud Data for Satellite Ground Optical Networking. My report will cover the following aspects, and in the first part of the report, I'm going to begin with the background and purpose of our work. Optical communication is one of the most promising communication technologies for the future space network. Compared with the traditional communication technology, optical communication uses optical beams as a carrier, which can not only realize high transmission rates, but also achieve better anti-interference performance. This characteristic of optical communication allows it to be applied to downlink Earth observation data from LEO satellites, or to transmit data to GEO satellites as feeder links. However, compared with the inter-satellite optical links, satellite ground optical links are subject to weather conditions, such as cloud coverage conditions, which will seriously attenuate the optical signal and even directly interrupt the optical links. Now, an effective strategy to solve this problem is to use multiple ground stations to form an optical ground station network. When some ground stations are covered by clouds and can't communication, set diversity guarantees one or more ground stations with cloud-free line of sight to maintain the optical communication and avoid communication disruption. Therefore, the selection of ground stations for an optical ground station network is particularly important for improving the availability of satellite ground optical networking. Our work is to solve the problem of how to select it of ground stations. In order to achieve OGS set selection, it's necessary to get the cloud coverage data over each candidate ground station. This paper proposes a method to process cloud data more effectively, which can determine the range of clouds that affect satellite ground optical links for 13 ground stations. Next, I will introduce how we use and process the real cloud data. Considering the location of our candidate ground station, we selected the HimAwai-8 GEO satellite to get the real cloud data. This figure shows the observation range of the HimAwai-8 GEO satellites. The resolution of cloud mask product is 5,500 times 2,200 pixels, where the spatial resolution is 2 kilometers and the temporal resolution is 30 minutes. The latitude and longitude information of a ground station can be used to find which pixel correspond to this ground station. And then we can finally get the cloud coverage data over this ground station. However, satellites are seldom directly above ground stations. The more common case is that the optical link between a satellite and the ground station maintain an inclination with the normal direction of ground. Therefore, the factor that really affects optical links is not the cloud directly above a ground station, but the cloud at the intersection of the cloud layer and optical links. Furthermore, a ground station usually communicates with multiple satellites, so a ground station can have more than one optical link. Therefore, the cloud area that affects optical links of satellite-ground communication is a range rather than a point. In this case, all the cloud data in this range must be considered. Considering the characteristic of optical links, we suppose that an optical ground station is available for communication only if it has an optical link with the elevation angle to the satellite of more than 20 degrees, and the satellite ground optical link is not blocked by clouds, as shown in this figure. The height of cloud layer is assumed to be 10 kilometers. Therefore, the range of cloud data that we need to consider for this ground station is the circular area with the radius of 27.47 kilometers, which needs to satisfy the following formula. Then, we average all the cloud data in this circular area. Finally, the processed data is regarded as the cloud data correspond to this ground station. Next, I'm going to introduce an effective method to achieve the optimal OGS network based on the calculation of network availability. As described before, through the processing and using of real cloud data, we can get the cloud coverage data of each candidate ground station. For each candidate ground station, we construct a cloud data vector CI. There are NS elements in this vector, which represents that the number of sample data points is NS. The data we obtained is sampled by HimAwai-8 GEO satellites every 30 minutes, and we use the data of 1 year to calculate the availability. So the number of elements NIs of each cloud data vector is 70,520. And each of these elements is binary. If it's 0, it means there's no cloud over the sky and the station is available. Otherwise, it means there's cloudy over the OGIs and the station is unavailable. Suppose the number of ground stations in the OGS network is n, and there will be n cloud data vectors. So we use each of these vectors as a row to form a matrix. So we can get the cloud data matrix C, whose size is n times NIs. Therefore, for a given network I, which including n OGIs, the number of available ground stations at time simple g can be calculated as the first formula. In order to calculate the availability, in addition to define the parameter n, we also need to define the parameter I, which represents that the required number of OGIs. That is, the network is available when at least M stations are available. Then, if AJ is greater than or equal to I, set the redefined AJ to 1. Otherwise, set it to 0. So the availability of OGS network can be calculated as the second formula. When we have a certain number of candidate ground stations, we only need to calculate the network's availability for each possible combination of ground stations. The combination with the highest availability can be regarded as the optimal OGS network. That is, the ground station set selection results under the parameter n and I. Now, by using the BeiDou method, we can get the result. First, we selected 15 candidate ground stations as shown in Table 1. The method described before can be expressed by this flowchart. We calculated the range of clouds that affect satellite ground optical communication for these candidate ground stations by the method in Section 2. After that, by processing all the cloud data in this range, we can obtain the cloud data vector of each candidate ground station. And then, the cloud data matrix C can be constructed. Finally, the matrix is used as an input to the network availability calculation method. As described before, the other two inputs are parameter n and I, where n is the number of ground stations that make up the network, and I is the number of ground stations that are required to be available. For different parameter n and I, by using the method in Section 3, we calculated the availability for each OGS network combination formed by these candidate ground stations, and the network with the highest availability is considered as the optimal OGS network. For the above candidate ground stations, the ground station set selection results and the max network availability under different n and I are as follows, where the ground station in the selection result is indicated by its number. In conclusion, in this paper, we propose a method to determine the range of clouds which affects satellite ground optical links for certain ground stations. By calculating the availability for all possible networks bound by 15 candidate ground stations, the network with the highest availability is chosen as the best optimal ground station network. Finally, we obtained the set selection results of optical ground station network for mainland China. Thanks for your listening.
Hello everybody, I am Huiwen Chen. The title of my paper is an Interdomain Routing Protocol, New BGP for Space Internetworking. The whole presentation consists of 5 parts. Next is introduction. Typical satellite networks include GEO, MEO, LEO, and other satellite systems. In space networks, each satellite system is generally regarded as an independent and complete autonomous system domain. As shown in the figure above, router 1.1 and router 1.2 in AS1 are selected as the boundary router of this domain to establish interdomain links with router 2.1 and router 22 in AS2. Considering the characteristics of the space environment, because of the orbital dynamics of the satellites, predictable link interrupts often occur, which will cause a huge consumption of the limited onboard resources. Moreover, there are also unpredictable link interrupts, which are usually caused by radiation interference of the communication channel or the temporary failure of a satellite. The special situations, as mentioned above, in space internetworking will bring a series of challenges and boundaries to the satellite networks with limited bandwidth. As an interdomain routing protocol, BGP is responsible for the routing among different AS domains, and the routers in different domains maintain the exterior boundary gateway neighbor relationship with each other, which called eBGP neighbor. And the BGP adopts a finite state machine in which the router starts from the idle state and to the connect state, to the open send connect state, to the open confirm state, and at last to the established state. In this situation, the BGP exchanges a series of messages, successfully establishing the neighborhood body relationship, as shown in the figure above. In this situation, time for detecting the link interrupts is too long, which will cause a lot of problems. Take the topology in the figure above as an example. Interdomain link between the border routers A and D breaks unpredictably. If link interruption time is short, the relationship between A and D will not change during the link break. So, during this interruption, all the transmission packets from router E to router F will be lost. If the link is interrupted for a long time, and the link is still not recovered when the neighbor relation between A and D is closed, the border routers A and D will declare the route prefix on the whole networks, and the route will be convergent and updated again, which causes a lot of time and resources. This is not only affects the stability of the network, but also wastes the limited onboard resources. To solve the problem, in new BGP, the traditional BGP never state machine is improved with the introduction of a new detection mechanism. On the border routers, test messages are sent every 10 seconds regularly to detect the state information of interdomain links. Once the neighbor does not receive the test messages, it judges that the link is done and modifies its own routes to the backup path. When it detects the link recovery, it returns to the established state from the backup route state. To detect interruptions, unpredictable link interruption can be divided into two types. The first type is that if the link interruption is short, then the neighbor relationship of neighbor body of each interdomain link will not change. It will turn to backup routes after probing, and then turn to main routes after recovery. The second type is that if the link interruption time is long, the eBGP neighbor relationships will come to an end, and the routes will change to the idle state. It will turn to backup routes after probing, and the connection of neighbors was closed. When the connection of neighbors was established, and it would then update routes. The calculation of backup route is mainly aimed at the next hop, and the next hop is modified as the backup route. The backup routing mechanism of the new BGP consists of the following steps. Firstly, a table of an interdomain topology relation is introduced, which records the bounder routers in AS1 and AS2 in real time, as well as the relations between them. There are bounder router A and B in AS1, and bounder router D and C in AS2. And there is an interdomain link between router A and D, and an interdomain link between B and C, as we can see in the table 1. Secondly, there are 3 destinations in AS2 to router A in AS1. Each destination is described as a prefix. To arrive each destination, router D will be its next hop, which is the same as described in the following table 2. In AS1, there are 2 destinations except router A, and to reach router E or B, next hop is also shown, as in the following table 3. Third, backup FIB is summarized as mentioned above in table 4. The principle of the calculation of the backup route is the first one. For any routing table item, if and only if the next hop is the eBGP neighbor node of the router, the corresponding backup route is generated. For any backup route, destination router and destination backup router are in the same AS. Main modules of new BGP protocol are shown in the figure above. The start module mainly completes the initialization. The event queue management module mainly manages the time queue. And second, the command processing module is responsible for processing various commands and calls, related functions for processing. The timing processing module handles the event timeout and other behaviors through the timer queue, detects the link state through the timing processing module, and then turns to the backup routing mechanism. The module of finite state meshing is responsible for the management of finite neighbor state meshing. Compared with the traditional BGP protocol, new BGP not only can deal with predictable interrupts, but also can deal with unpredictable interrupts, greatly reducing the routing convergence time and rapidly detect link interruption. In this part, the performance of the proposed new BGP will be verified in the case of unpredictable link interrupts, especially with the comparison with the traditional BGP protocol. Take the test topology as an example. In this topology, there are 2 AS domains, each containing 4 router nodes and 2 boundary routes. There are altogether 4 boundary routers in the whole topology, 2 of which are eBGP neighbor bodies of each other, and there are 2 interdomain links between the 2 domains. In order to simulate space environment and verify the validity of the improved interdomain routing protocol, it uses Docker and the software router Quagga as routers. At the same time, the routers are connected by OVS, and it uses OVS flow table to simulate link interruption and recovery. Considering the impact of link interruption time on performance, different lengths of the link interruption time are selected here as independent variables to test the performance. In this part, to analyze the performance, three metrics are selected to evaluate the performance of the new BGP and traditional BGP protocol, which are the detection time of the unaccepted link interruption, the routing convergence time, and the network stability. As we can show in the left figure and the right figure. In the left figure, the link interruption time is selected from 5 seconds to 360 seconds, and each 5 seconds is a step length. When the unpredictable link interruption duration is less than 118 seconds, it can be found that the link interruptions cannot be found by the traditional BGP protocol. When the time is more than 118 seconds, the traditional BGP protocol can detect the interruption, but the time is from 120 seconds to 180 seconds, which is a little long. And in the right figure, as we can see, in contrast, it can be found that the link interruption can be detected by the new BGP quickly after about 10 seconds, and the detection speed is much faster. The route convergence time is mainly composed of two parts. The first part is the route convergence time from the detection of link interruption to the end of route convergence. The second part is the route convergence time from the link recovery to the end of route convergence. As we can see in the figure, in traditional BGP protocol, the convergence time is about 0 to 7 seconds. And in new BGP, as we can see in the right figure, the convergence time is about several milliseconds, which is much shorter than convergence time in traditional BGP. At last, it turns to network stabilization. As we can see in the figure, it can be found that the network stability of the BGP protocol is poor, which is less than 50%, and increases gradually with the increases of link interruption duration. However, in contrast, the new BGP protocol has better network stability, which increases rapidly with the increases of link interruption duration and maintains about 100% in a long range. Finally, it comes to conclusions. In this paper, new BGP adopts the MininetE BGP protocol and introduced a new detection mechanism to detect the interdomain link interrupts at a faster speed. And on the other hand, considering the predictability of orbital dynamics of the satellites, a backup routing mechanism is introduced to guarantee the corresponding backup route on the boundary router. The future research will be focused on how to reduce the routing cost as well as shorten the routing convergence time and improve the routing stability. That's all. Thank you.
Hello everyone, I'm Zhiyong Zhang from Nanjing University. Today, the topic of my report is Infrared Cloud Imaging System for Laser Satellite to Ground Communication. The report has three parts. The first part is the background and significance of the infrared cloud imaging system. First, as the demand for space-state communication continues to increase, traditional satellite-to-ground communication technologies has been able to meet the increased demand for data transmission due to relatively low transition rates. The use of laser communication technology has become the development trend of future satellite-to-ground communication. The establishment condition of the optical communication link is almost an abstracted atmosphere path, but the most critical obstacle is the influence of the cloud. Thin clouds will alternate the optical signal with optical characteristic, while thin clouds will completely destroy the optical signal. Therefore, the weather mode should be selected for the location of the ground station, especially the cloud distribution is irrelevant or anti-correlated. The general process of the infrared cloud image system is divided into the following parts. The first is to use a long-wave infrared camera to image the sky. Then, perform radiometric calibration on the acquired gray-view image to obtain the sky-reduced image. The third step is to eliminate atmosphere radiation and get the video radiation image. The fourth step is to detect and clarify the clouds of the remaining radiation image. Finally, combined with the situation of the communication link. The second part is system design. This is a prototype of the infrared cloud image. It is mainly composed of three modules: optical module, temperature control module, and communication control module. First, the core of the optical module of the infrared cloud imaging is the FLIR Tau-2 microwave below-meter camera, which is used to scan the downward infrared radiation of the atmosphere in the 8 to 14 mm band and can provide a 110-degree diagonal field of view. The applicable temperature range is below 40 to 80 Celsius. Using the temperature sensor inside the camera, the real-time temperature information of the camera can be read from the camera serial port through a microcomputer. When the temperature of the camera reaches a predetermined ampere threshold, the temperature controller will automatically enable the built-in TEC caller in the case to call the inside of the case, and use a fan to maintain air circulation inside the case to keep the temperature of the camera at about 25 Celsius. The communication control module is used to control and obtain the camera shooting data. Using the server client mode, it can accommodate multiple users to access the server and download real-time data at the same time. Users can set the time interval for shooting cloud image according to their words, their own needs, and send the captured observation data to the local client via the server in 8-bit PNG format. The last part is data processing. This camera is an uncoded focal plane array camera. It has many advantages in its use. The first, the size of the camera has been reduced. The second, first, it has fast startup time and very low power consumption and last low cost. But the problem with this type of camera is the camera's scan radiation output is affected by the temperature of the focal plane area. In order to solve this problem, we conducted some experimental research. First, verify the problem with the camera. We placed a flare Tau2 camera and a blackbody source in an environmental chamber. The temperature in the environment chamber rose from 15 to 35 Celsius, and the temperature of the blackbody was maintained at 10 Celsius, 20 Celsius, and 30 Celsius, respectively. So look, the red line indicates the change of the camera's response to the blackbody source as the ambient temperature gradually increases. The blue line represents the output response when the camera focal plane area temperature stabilizes at 25 Celsius. The figure of the left shows the actual temperature corresponding to the dN value of the camera responding output. The figure of the right is the result of 3 fittings. So, we can know that as the temperature of the camera focal plane area increases, the radiation response to the blackbody's scan decreases. Here is the relevant formula derivation. So, the black line is the date before calibration, and the red line is the date after calibration. The blue line is the output response when the camera focal plane area temperature stabilizes at 25 Celsius. After calibration, the camera's scan radiation response actually reaches about 95%. Thanks.
Hello everyone, I'm Wu Guangyu from Nanjing University of Aeronautics and Astronautics. It is an honor for me to introduce you our recent work, Collaborative Interference Source Search and Localization based on Reinforcement Learning and Two-Stage Clustering. The presentation is divided into 4 parts. Firstly is the introduction of our work. Interference sources not only illegally occupy growing spectrum resources, but also have brought grave implications to many fields, such as railway communications and broadcast channel. Thus, an efficient and accurate search and localization method to locate interference source had become an urgent demand. Exploiting unamended aerial vehicles to locate the position of interference sources have attracted intensive research interests due to UAV's flexibility and the feature of suffering less multipath interference. Some methods realize localization but need a priori knowledge, such as transmit power and propagation parameters. Reinforcement learning methods, on the other hand, can realize precise localization without priori knowledge, but require an UAV to keep searching until it arrives at the interference source. In real life, locating interference source suffers from unknown but dynamic surroundings. Despite from accuracy, time efficiency is also an important index for interference source localization. Furthermore, when we consider remote localization, the result might be affected by multipath effect. Against this background, we aim at designing a time-efficient and accurate approach which applies a swarm of UAVs to search and locate a certain interference source without any priori knowledge of the interference source model or the noise model. And a novel collaborative search and localization approach based on reinforcement learning and two-stage clustering is proposed. In the proposed system, as is shown in the figure, we employ a swarm of UAVs to locate an interference source. In the UAV swarm, each UAV is equipped with an electronic scanning antenna which can be used to measure power of received signals from different directions. We assume that in the swarm, each UAV flies in a straight line between 2 adjacent time intervals and stays at a constant altitude. Thus, for a certain UAV, its coordinate is only relevant to its step length, the flight direction, and its coordinate at the last time interval, which is shown in the frame. In the study scenario, each UAV is equipped with a 3-dimensional electronic scanning antenna to measure power of received signals from horizontal as well as vertical directions. Each electronic scanning antenna is able to measure U horizontal directions and V vertical directions. UAVs fly at a constant altitude and directions of flight vary only in the horizontal plane. Therefore, given a horizontal angle, although the power of signals from different vertical angles can be different, only the maximum can be applied to make decisions on the horizontal direction of flight. We now give the scheme of our collaborative search and localization method. In the proposed method, the search and localization could benefit from synthesizing the individual decisions within a swarm of UAVs. Briefly, a searching phase and a localization phase are alternatively performed. In the search phase of every iteration, each UAV in the swarm decides the direction of flight in the next time interval by performing reinforcement learning. The instant reward of reinforcement learning can be related to the power of received signals which can be emulated by the interference source. Hence, the direction of flight which is determined by the reinforcement learning can be a possible direction of interference source. By performing such reinforcement learning algorithm at each UAV in the swarm, the UAVs can search and fly towards the interference source. Moreover, as each UAV flies in a straight line between 2 adjacent time intervals, the extensions of the trajectories of 2 UAVs might intersect, where the intersection is essentially a possible position of the interference source. Due to the fact that The searching might suffer from noise and possibly multipass effect. The intersections might shift. To find out the potential position of the interference source, the two-stage clustering algorithm is proposed during the localization phase. The two-stage clustering algorithm first clusters the intersections and make a decision whether to move a certain intersection to the candidate cluster. Then, by performing the secondary clustering, the position of the interference source can be estimated. The search phase and the localization phase will implement until the estimated position meets the determining condition. In the search phase, in order to reduce the effect of noise on measured power, we take the average power value as the reward of the reinforcement learning. The reinforcement learning algorithm is based on Q-learning, and in order to accelerate the convergence of Q-learning, we simultaneously update action values with virus action for a given state. Once action values are updated, the optimal action for each UAV is corresponding to the maximum power value at such state and indicating the flight direction at the present time interval. After action is chosen at a certain time interval, each UAV flies in its direction for a constant distance. For a certain pair of UAVs, the extensions of their trajectories can intersect, as is shown in the figure, and the weight is defined in order to evaluate the offset of the intersection to the interference source location. The intersections, along with their weights, form a candidate set and is used as the input of the two-stage clustering algorithm for localization. The intersection in the two-stage clustering algorithm, firstly, we formed a weighted matrix indicating the distance between each two intersections. Each row of the matrix is firstly ascending sorted in order to get the nearest intersections for each intersection. A metric is defined for each row in order to evaluate the possibility that a certain intersection is equal to the coordinate of the interference source. We then compute the centroid of the potential coordinates as a result of the weighted clustering at the certain time interval. In order to further improve the accuracy of localization, we propose the method of secondary clustering. In the proposed secondary clustering, a candidate Q is defined. Once the weighted clustering achieves and estimates the interference source position at a certain time interval, the estimated position is pushed in the candidate Q for secondary clustering. Specifically, if the candidate Q is full, the head of the Q will be popped as it has the least possibility of equaling to the coordinate of the interference source. Similar to the weight matrix in the weighted clustering, a distance matrix is also computed with the element in the candidate Q in the secondary clustering. In the matrix, each element equals to the distance between arbitrary two coordinates in the candidate Q. Each row of the matrix is firstly ascending sorted before being given a metric to evaluate the possibility that a certain intersection is equal to the coordinate of the interference source. The centroid of the corresponding points to the row scored the highest matrix will be computed similarly to the weighted clustering. The proposed two-stage clustering determines when the last three estimated coordinates satisfy the terminate condition as is shown in the frame. And we now give the simulation results of our work. The following three figures compare the localization performance of the proposed collaborative interference source, search and localization method based on reinforcement learning and two-stage clustering with two other baselines, specifically the Q-learning method and the Maxim RSS-based search with two-stage clustering-based localization. The figures intuitively shows that the proposed method can locate the interference source accurately from a remote distance and got the best performance. We also compare our method with the two baselines in different index. From the first figure in the frame, it shows that the proposed method can achieve a high accuracy compared with two other baselines, and in figure two, and in the second figure, it shows that our method can locate the interference source from the longest distance. And in the last figure in the frame, it shows that our method takes the least time before the swarm of UAVs locates the interference source. In summary, in this paper, we developed a novel collaborative interference source search and localization method based on reinforcement learning and two-stage clustering. A new scheme is proposed, merging reinforcement learning-based search and collaborative remote localization for a swarm of UAVs to locate an interference source. We also gave a low complexity reinforcement learning algorithm for each UAV in the swarm to decide and evaluate its own direction of searching. And we also realized a novel two-stage clustering algorithm to find out the potential position of the interference source. And that is all for our work. Thank you very much.
Hello everyone, my name is Hao Yun. It's a great honor to be able to participate in this meeting. The topic I want to report is a new-zone tracking method of BeiDou B1C signal and influence on signal quality evolution. Before starting, please allow me to introduce the background of the topic. Aiming at the problem of low accuracy of traditional open-loop tracking and long time consuming of closed-loop tracking. Its people propose a joint open-loop and closed-loop tracking method of BeiDou B1C signal, which not only ensures the tracking accuracy but also generally reduces the time consuming of signal track. I will introduce from the following 5 aspects. Part 1. Research background and signal characteristics of BeiDou B1C. As the link between satellite and the user, the performance of the satellite navigation signal directly determines the service performance of the satellite navigation system, such as positioning, navigation, timing, and so on. Navigation signal quality monitoring and evaluation can provide important technical means and support for navigation system, signal design, and key technology, on-orbit verification, and provide decision support information for system performance. Maintenance and management. The navigation baseband signal quality evolution contains the following aspects: time domain performance contain I. The frequency domain performance contain power spectrum is estimation spectrum distance. The modulation domain performance contain constellation, amplitude, balance, and IQ phase organality. The related domain performance contain related loss, related function, and their crossing division of S-curve. This figure shows the distribution of signal frequency bands of each GNSS system. To release the interoperability with GPS L1C and Galileo E1 OS signals, the BeiDou B1C signal adopt QM-bulk modulation. The power spectral density and autocorrelation function of QM-bulk signal are the same as of TM-bulk signal. Compared with the TM-bulk modulation signal, the receive of the QM-bulk elevators the switching circuit of time division, multiplexing locally, and they have the same performance and the condition of matching reception. The B1C signal is no longer a single signal, but a composite signal containing data and pilot channels. Among them, the data channel modulation has navigation message data, which can be used for prudent measurement and navigation information solution. Whereas the pilot channel doesn't modulate navigation information, but it's only composed of spread term code modulated by the carrier. The B1C signal baseband from can be expressed as shown, where date is the navigation date stream, CDT is the date component, spread term code. CPT is the pilot component spread term code. Part 2. Open loop and closed loop tracking principle. The input signal is acquired by traditional acquisition to obtain rough Doppler frequency and code phase estimation value. The least square equation is used to fit the quadruple binomial, and the peak value of the fit curve is selected as a question value of the Doppler frequency and code phase. The modified Doppler frequency, code phase, and the carrier phase are output to the subsequent bit frame and other processing modulus as a result of the open loop tracking. For the estimation of the Doppler frequencies, it can be seen from the formula of complex coherent integral value that the profile of coherent integral value as any code phase is the result of function superposition noise through the quadratic of linear lattice square. Fitting is used for parameter fitting. After the satellite signal is captured, the rough estimators of carrier frequency and the code phase of the current satellite signal are obtained. However, due to the change of Doppler effect caused by the relative motion between satellite and the receiver and the change of relative acceleration, as well as the frequency offset between satellite clock and the receiver clock, the carrier frequency and code phase of the received satellite signal will change, unpredictable with time. Therefore, it's necessary to process the satellite signal in the loop. It's code tracking and carrier tracking. A specific tracking principle is shown in Fig 3. In the stage of carrier loop and code loop stating the data of one mine code circle length is read each time for date length, and finally the carrier phase difference is obtained to adjust the local reference signal of each loop and the receive signal phase time to be consistent. The advantage of closed loop in tracking is that the data of each mine code circle length is frequently discriminated against to ensure a high tracking accuracy. Part 3. Open closed loop joint tracking mode. To ensure the tracking accuracy and improve the operational effectiveness and to the greatest extent, its people propose an open closed loop joint tracking method based on the advantages of open loop tracking and closed loop tracking. For the convenience of explanation, referred to as joint tracking, the tracking principle is shown in Fig 4. The loop control principle is shown in Fig 5. First, set the open loop interval according to signal characteristic and data quality. For example, 100 millisecond. The loop input signal SIF first set the tracking mode adopted by the date of the period length of the mine code through the loop controller. If the open loop tracking is adopted, the loop output parameters of the previous closed loop tracking will be assigned to the current open loop tracking. If the closed loop tracking is adopted, the normal tracking will be conducted according to the flow shown in Fig 3. And finally, a complete loop will be formed. Generally, since the difference of carrier phase and the adjustment parameters of the code loop are very small for the date of tens of hundreds of milliseconds, after the signal into the stable tracking state, a loop controller can be adapted to the feedback loop of the code loop and the carrier loop to realize the joint tracking of open loop and closed loop tracking. Because the frequency discrimination times of carrier loop and the code loop are reduced, the tracking time of the signal is greatly reduced. Part 4. Mine parameters of signal quality evolution. The distance of the received navigation satellite signal tape waveform is not only reflected in the amplitude attention of the correlation output, but also caused the deformation of the correlation function. The pseudo error caused by the distance of the received signal can directly reflect the abnormality of the correlation function. Using the correlation curve, we can evaluate the correlation power loss caused by channel band limit and distance of and its influence on navigation performance. The lower the correlation loss, the higher the pseudo measured accuracy, and the lower the receiver threshold. When using the above formula to calculate the correlation loss, we should also consider the influence of the received relative change of power distribution between different bandwidth signal components caused by the actual band limited filter on the calculator results. Theoretically, the zero crossing point of the receive code loop frequency discrimination curve, as is the lock point of the code loop, should be located at the point where the code tracking error is zero. In fact, due to the influence of channel transmission, distortion, and multipass, the frequency discrimination curve of the code loop is often located in the places in phase derivation. By evolution, the constants of region code purient and carrier phase purient. The relative delta between code and carrier in the modulation process of satellite navigation signal is measured. Because the output value of the carrier phase observation of the receiver is not the absolute carrier phase out, but related to the relative carrier phase output at a certain time, and the consistent evolution is mainly to evaluate the relative stability of the code and the carrier phase. Part 5. Experimental results and conclusions. A signal tracking process is mainly composed of carrier and pseudocode separation, loop phase discrimination, and filtering. And the time value of joint tracking and closed loop tracking is about 1 to 10. The separation process of carrier and pseudocode is the most computationally intensive and takes up the most time. The total time of joint tracking is 4.554 seconds, and the total time of closed loop tracking is 45.535 seconds, which save about 90% of the time compared with closed loop tracking. Compared with the closed tracking, the overall trend of the output value of the loop discriminator and the output value of the loop filter in the open-closed loop tracking method is basically consistent with that of the traditional closed-loop tracking method, which shows that the method can realize the stable tracking of signal. To analyze and compare the symmetry, sameness, and constant degree of the curve, the whole correlation curve is moved to zero tip from the comparison of this thick. It can be seen that the joint tracking method basically coincides with the correlation curve of the traditional closed loop tracking. Figure shows the correlation loss figure of each component calculators data once every 50 milliseconds in two tracking methods with a total of 20 times. The horizontal line with the value of 0.3 represents the evolution index. Take the mean value and get a correlation loss evolution result in tip 3 through correlation calculation. Figure above shows the zero crossing derivation of the S-curve of each component in two tracking methods. The difference between the mixed value and the mean value of the curve in this figure is the zero crossing derivation of the curve. Peaks no summit result in a large range derivation, which will be abandoned as the evolution index. Tip 3 shows the mean value and the standard deviation of the zero crossing derivation of S-curve of each component in two tracking methods. It can be seen that the difference between the two tracking method of each component is very small and the curve constance is high. The research result shows that 1. Under the condition of the same mirror signal and the same receiver tracking parameters, the data length ratio of the open closed loop tracking of joint tracking is 1 to 9, and the tracking time of the open closed loop joint tracking method is about 90% less than the traditional closed loop tracking method. 2. The mean and standard duration of the difference between the T2 correlation curve are very small, and the degree of curve constance and the symmetry of the left and right overall are relatively high. 3. The change range of correlation loss value of the two tracking method is within 0.4%, and the difference between them is very small, and both are less than the 0.3 dB index requirements in the BeiDou ICD document. 4. The constance degree of SCB curve of the two tracking method is very high, and the value range of SCB is within 0.7%, which meets the index requirement of 0.5 nanosecond. There is basically no difference between the code and the Korea phase constance mean result of the two tracking method. Therefore, the open closed loop joint tracking method proposed in this paper can generally improve the efficiency of data processing based on ensuring the tracking effect. Thank you.
Hello everyone, my name is Dai Zhun, coming from Nanjing University. My report topic today is the cloud change prediction system based on deep learning. It's mainly composed of 4 parts. Let's first focus on laser communication. It is mainly method of communication technology in future satellites to satellites and satellites to ground in space networks. Compared with traditional microwave communication technology, space laser communication takes the advantages of using laser as a carrier, which can realize a large data transmission at high speed and has high anti-interference and confidentiality. However, the problem we encounter is in satellite-to-ground laser communications. The laser beam is susceptible to the effects of atmospheric media when it passes through the atmosphere. The main reason is that the laser beam will be absorbed and scattered by the cloud when it passes through the cloud, causing the communication link to be blocked. Therefore, in order to know the cloud coverage information around the laser communication link in advance, it is necessary to predict the change trend of the cloud over the ground station in advance. If there is no cloud through the link for a period of time at present and in the future, the link can be established directly. After the link is built, if it is predicted that a cloud will pass after a period of time. It can be judged whether the cloud is thin or thick. If it is a thin cloud, the robustness of the link can be enhanced by changing the modulation and other methods. If it is a thick cloud, we can only switch to other ground stations, all for the purpose of uninterrupted communication. Therefore, it is necessary to predict in advance the trend of cloud clusters over the ground stations. The extrapolation methods commonly used in radar image prediction mainly predict radar images on the premise that the system remains stable, such as linear forecasting methods, cross-correlation methods, and single-centered methods. For linear forecasting methods, it has been rarely used as most of the actual scenarios are non-linear problems. For cross-correlation method, it simply predicts the cloud cluster position at the next moment by calculating the cross-correlation coefficients of two adjacent images. However, due to the inherent disadvantages of cross-correlation method, the algorithm's forecasting ability rapidly decreases over time. The monomer-centered method is suitable for the target monomer that is easy to identify. For the application scenario of this paper, the cloud in the atmosphere will be deformed or disappear, and new clouds will be generated. So the cloud cannot be used as a single-centered model. Since traditional prediction methods cannot meet the needs of our scenarios, the rise of deep learning in recent years has provided us with another way. In the case that the traditional extrapolation methods have their own shortcomings, this paper proposes a solution, CloudNet, whose workflow is shown in Figure 1. Including a classification model and an unsupervised prediction model, which both based on deep learning for predicting the trend of cloud cluster in the airspace through the laser link. We attempt to divide the cloud sequences into categories. Fewer clouds and cloudy according to the degree of cloud cover by threshold of 1/3 due to the amount of cloud over the link will directly affect the prediction result. Furthermore, we treat stratiform clouds as a separated category and have the highest classification priority, as the stratiform clouds are evenly curtain-like, with a large range and long duration among all categories of clouds, which are differently from others. When we choose the classification model, we screened out 3 plans in the early stage, namely VGG16, ResNet, and Inception. Due due to VGG16 has fewer parameters, shows a graceful accuracy in the fields of image classification and object detection, and the usage of scenario is more lightweight. We finally extract features from cloud image sequences using VGG16 model, whose structure is shown in Figure 2. When the classification is completed, we need to make predictions. The deep PresNet model is improved based on convolution LSTM model with increased stake layers from 4 to 6 and enlarged kernel size from 3 multiply 3 to 5 multiply 5. For large state-to-state kernels are more suitable for capturing spatial temporal correlations. The input sequence is input from X, and the prediction results is output from Y. Each layer is composed of 4 basic modules: an input convolutional module AL, a recurrent representation module RL, a prediction module AL hat, and an error representation module EL. As the figure shows, these modules stacked in a certain relationship instead of simple linear stacking of convolutional LSTM. The representation layer RL is a recurrent convolutional network that can generate a prediction AL hat of what the layer input AL will be on the next frame. The network takes the difference between AL and AL hat and outputs an arrow representation EL, which is split into separate rectified positive and negative arrow populations. The arrow EL is then passed forward through the convolutional layer to become the input to the next layer. The recurrent prediction layer RL receives a copy of the arrows EL along with top-down input from the representation layer of the next level of the network. Here is the update algorithm. The status is updated by 2 steps. First, the RLT state is updated by the top-down path. Then the ALT hat, ALT, and the ELT states are updated by forward paths. RL and EL are initialized to 0 on the account of the nature of the convolutional network, indicating that the original predictions are spatially uniform. We collected the cloud image sequences over a specific area in Nanjing in March, with the cloud infrared camera independently developed by our research laboratory. The infrared camera collected more than 30,000 cloud images as a basic dataset cloud image by taking pictures every 5 seconds, all of which are grayscale images with a resolution of 720 multiply 480. It is shown in figure above respectively that the prediction results of using PSATS model and CloudNet model, where figure A to C are full cloud, cloudy, and stratiform cloud image sequences respectively. In each image sequence, the first row is the ground truth of cloud image sequence, while the second row is a predictor cloud image sequence based on the previous timestamps. By comparing the predictor images, we can see that both two models can predict cloud image sequences under all three conditions. The prediction results of the PSATS model are significantly different from real images in the last several images. In comparison, the prediction result of CloudNet is more consistent with the ground truth. Table 1, 2, 3 respectively calculate the mean square error and accuracy of the prediction results of PSATS and CloudNet on three conditions of field cloud, cloudy, and stratiform clouds. According to the prediction results, CloudNet can predict the cloud status at the next moment more accurately than PSATS. The prediction average accuracy is up to 81 with a 100 seconds prediction interval and a tolerance of 5% error per pixel. Therefore, we use the CloudNet model that is superior to the other model as the first choice in the scenario of cloud trend prediction on the satellite to ground laser communication link. This paper takes the influence of atmospheric cloud cluster on satellite ground laser links as a starting point, and we have successfully applied the deep learning to the challenging cloud forecasting problem. We made two cloud datasets and proposed a cloud prediction system, CloudNet model, based on the extension of PSATS to tackle the problem. By incorporating classification model and prediction model into the system, we built an end-to-end trainable model suitable for different weather conditions over the ground station. For future work, we will make a more detailed classification of cloud categories according to meteorology. Besides, more researches will be done on how to improve prediction time, such as taking all sky cloud image sequences as dataset, for it has a longer time span. Thank you for listening.